In the vast expanse of the cosmos, unimaginable and awe-inspiring events unfold, with explosions that defy comprehension, shedding light on the darker and more terrifying facets of the universe. Imagine witnessing an explosion so colossal that it outshines an entire galaxy, casting an intense glow that could rival the brilliance of all the stars in a galaxy combined. This is the reality of supernova explosions, a breathtaking yet terrifying spectacle marking the death of a star. These events are not only powerful, but carry profound implications that ripple through the universe. The brilliance emitted by such an explosion can stretch across vast distances, leaving behind a cosmic legacy that we can only begin to understand. But these supernovae are just one facet of the overwhelming power contained within the universe. The cosmos is a domain where the extraordinary and the terrifying exist side by side, creating a constant cycle of birth, death, and rebirth. From the cataclysmic fury of gamma-ray bursts to the mysterious formation of black holes which consume everything in their path without a trace, space holds boundless potential for both awe and fear. Events in space unfold with breathtaking speed, as rogue planets drift untethered through the dark expanse, unbound by the gravitational pull of a star, forever lost in the cold vacuum of space. Cosmic collisions, on the other hand, bring new celestial bodies into being, while also shattering old ones, reminding us that the cosmos is never static. It is in constant motion, transforming and evolving in ways that we are only beginning to comprehend. As we venture into the mysteries of the universe, we delve deeper into the most terrifying events that await us. Supernova explosions, the cataclysmic deaths of stars, are some of the most powerful and luminous events in the universe. These explosions signify the final chapter of a star's life cycle. Imagine a star, a massive sphere of gas composed mainly of hydrogen and helium, undergoing the ceaseless process of nuclear fusion at its core. This fusion generates vast amounts of energy, which produces an outward pressure that balances the inward pull of gravity, preventing the star from collapsing under its own weight. For millions, even billions of years, this delicate equilibrium maintains the star's stability, but eventually the star exhausts its nuclear fuel. For massive stars, this process leads to the formation of heavier elements within the core. As the star progresses through its life cycle, the core becomes filled with increasingly heavier elements. When the star reaches the point of producing iron, fusion comes to a halt. Unlike the elements that came before it, iron cannot undergo further fusion to release energy. This marks a critical turning point in the star's life. Without the energy from fusion to counterbalance the force of gravity, the star begins to collapse inward. The collapse happens incredibly quickly, compressing the core to a point of unimaginable density. At this point, the core becomes so dense that it cannot support its own mass, causing it to rebound in a massive explosion. This is the birth of a supernova. The result is an explosion so powerful that it releases more energy than our sun will produce in its entire lifetime. In fact, a supernova can briefly outshine an entire galaxy, shedding light and energy across vast stretches of space. The force of the explosion expels the outer layers of the star into space, creating an expanding cloud of gas and dust. The light and energy released during a supernova can last for weeks or even months, with the intensity fading over time. Yet it's not just about the light. Supernovae play a crucial role in seeding the universe with the elements necessary for the formation of new stars and planets. The materials expelled during the explosion, elements like carbon, oxygen, and nitrogen, are essential for the creation of new worlds. While the death of massive stars leads to the intense spectacle of a supernova, less massive stars do not meet such a dramatic fate. Instead of a massive explosion, their deaths result in the formation of a planetary nebula, a much less energetic event. However, the death of a massive star marks the spectacular conclusion of a life filled with nuclear reactions and cosmic transformations. The supernova and its remnants leave a lasting impact on the universe, forever changing the cosmic landscape. Supernova explosions are among the most extraordinary phenomena in the cosmos, a true testament to the raw energy and power that govern the universe. The death of a star is a violent and dramatic event that marks the end of one cosmic era, while paving the way for the creation of new stars, planets, and even galaxies. The beauty of a supernova lies not just in the energy and light released during the explosion, but in the intricate and colorful nebulae that often form from the remnants of these stellar deaths. These clouds of gas and dust are infused with elements forged in the fiery heart of the star, serving as the building blocks for future generations of stars and planets. Yet the terror of a supernova is equally profound. While these explosions give birth to new stars and planets, they can also bring destruction on an unimaginable scale. The intense radiation and shock waves produced during a supernova can have catastrophic effects on nearby cosmic bodies. In a galaxy populated with countless stars, the death of one can have far-reaching consequences. It can disrupt the orbits of neighboring stars, alter the trajectories of planets, and even trigger a chain reaction of supernovae. The consequences of such a chain reaction could lead to the formation of new stars, but at the cost of immense destruction, reshaping the galaxy in the process. And while the likelihood of a supernova occurring close enough to Earth to directly affect us is incredibly low, the potential consequences of such an event are far from insignificant. If a supernova were to occur within a few dozen light years from Earth, the radiation and energy released could have catastrophic consequences. The intense bursts of radiation could strip away our atmosphere, exposing life on Earth to deadly levels of ultraviolet radiation. This could be devastating to many forms of life, as our ozone layer is the planet's primary defense against harmful radiation from the sun. Without it, ecosystems would collapse, and life would face a struggle for survival. Furthermore, the shock waves created by the explosion would send ripples through space, generating cosmic particles that could reach Earth. These particles could interfere with satellite operations, disrupt electronic systems, and even endanger astronauts in space. The long-term effects of such an event could be just as profound. The radiation and particles from a supernova could alter Earth's climate, leading to significant changes in weather patterns, ecosystems, and the overall stability of the planet. The fact that we are so vulnerable to these cosmic forces highlights just how dynamic and unpredictable our universe truly is. Yet, even more terrifying than supernovae are gamma-ray bursts, which are considered the most powerful explosions in the universe. Gamma-ray bursts are caused by two primary events: the collapse of massive stars and the collision of neutron stars. When a massive star runs out of nuclear fuel, it can no longer support its own weight, leading to a catastrophic collapse. This collapse can trigger a supernova, but under certain conditions, it also creates intensely focused jets of gamma rays that burst outward into space. The other scenario that can lead to gamma ray bursts occurs when two neutron stars, dense remnants of supernovae, collide, sending out massive waves of gamma radiation. These bursts of gamma rays are so powerful that they can release more energy in a few seconds than our sun will produce in its entire lifetime. The radiation from a gamma ray burst travels at the speed of light, crossing vast stretches of space and impacting everything in its path. Astronomers detect these bursts using specialized space-based telescopes that are capable of sensing the high-energy photons produced during the burst. Instruments like the Fermi Gamma Ray Space Telescope are essential for observing gamma ray bursts, as Earth's atmosphere absorbs gamma rays, preventing ground-based telescopes from capturing them. When a gamma ray burst occurs, the instruments on these telescopes capture the intense radiation and record the burst's brightness, duration, and spectrum. By analyzing this data, scientists can learn more about the nature of these extraordinary events and gain insights into their origins. This information also allows astronomers to pinpoint the location of the burst in the sky, which is crucial for studying the afterglow of the burst, a phenomenon that provides additional information about the cosmic forces that caused the explosion. Despite the fascinating scientific value of gamma ray bursts, they also carry with them a potential threat to our planet. If one of these bursts were to occur within several thousand light years of Earth, and its radiation were directed toward our planet, the consequences could be catastrophic. The burst would unleash an unprecedented amount of radiation, potentially stripping away a significant portion of Earth's ozone layer. With the ozone layer gone, life on Earth would be exposed to dangerous levels of ultraviolet radiation from the sun, leading to widespread disruptions in ecosystems and a dramatic increase in skin cancers. The These cosmic events, the supernova explosions, the gamma ray bursts, and the terrifying potential of a nearby stellar death, remind us of the raw, uncontrollable forces that govern the universe. As we peer into the depths of space, we are confronted with the knowledge that our existence is fragile, held in place by a cosmic web of forces far greater than we can fully comprehend. The universe is a place of both awe and fear, where immense beauty and unimaginable destruction coexist in a never-ending cycle of creation and annihilation. Moreover, the energy released by a gamma-ray burst, GRB, one of the most powerful and violent events in the universe, could trigger a cascade of electromagnetic phenomena so intense that they might disrupt electrical grids, satellite communications, and much more. Such an event would not only wreak havoc on our technology, but could also present a dire threat to life itself. Animals that rely on Earth's magnetic field for navigation, such as certain species of birds, sea turtles, and migratory fish, could be disoriented, causing massive disruptions to their migration patterns. This would have far-reaching consequences for ecosystems and biodiversity, as these disruptions can severely affect species that depend on predictable environmental cues. When one link in the chain of life is disturbed, the effects ripple outward, leading to cascading consequences through entire food webs and ecological structures. While the likelihood of a gamma-ray burst occurring in such a way as to directly affect Earth is exceedingly low, the potential consequences of such an event would be devastating and transformative. Gamma-ray bursts are rare occurrences, but their sheer intensity means that even the smallest risk carries catastrophic implications. The intense radiation released from a gamma-ray burst could strip away the planet's atmosphere, effectively causing the loss of one of Earth's most critical protective layers, exposing the surface to extreme levels of harmful radiation. The very nature of this cosmic phenomenon means that it could disrupt life as we know it, altering our atmosphere and biological landscapes in ways that would be profound, irrevocable, and potentially fatal. Long-term effects of such an event could be equally, if not more, devastating. The immediate radiation from a gamma-ray burst might trigger mass extinction events similar to those that have shaped Earth's history after previous global catastrophes. Throughout the geological record, there are numerous examples of species being wiped out after dramatic shifts in the environment, such as the extinction of the dinosaurs following the asteroid impact some 66 million years ago. A gamma-ray burst could trigger similar levels of destruction, creating sudden and extreme changes in Earth's climate, atmospheric composition, and radiation levels. Species that cannot quickly adapt to these rapid changes could face extinction, while those that do survive might struggle in a changed environment, leading to an ecological collapse. In essence, while gamma-ray bursts may be exceedingly rare, the possibility of one happening and directing its lethal energy toward Earth carries with it the potential to reshape the entire course of life on our planet. It's a cosmic gamble we cannot afford to ignore. This is a force that could bring our ecosystems to their knees and alter the trajectory of life itself. The magnitude of the energy released in a gamma-ray burst, ranging from several thousand to potentially several million times more powerful than the sun's energy output, makes it one of the most extreme events in the universe. Its potential to permanently change the climate, the atmosphere, and the living organisms that depend on Earth's delicate balance cannot be overstated. To understand how humanity might protect itself from such an extraordinary cosmic event, it is essential to first delve into the nature of gamma-ray bursts themselves. A gamma-ray burst is, in essence, a colossal explosion that occurs in distant galaxies, releasing intense beams of gamma radiation. These bursts are thought to occur when a massive star runs out of nuclear fuel, collapsing in on itself and creating an incredibly powerful event that unleashes unfathomable amounts of energy. It's as though the universe is lighting a match to burn through vast swathes of space. Imagine a lighthouse beam cutting through the darkness of the ocean. This is how the radiation from a gamma-ray burst would look, except on a cosmic scale. If a gamma-ray burst were to be aimed directly at Earth, the consequences would be nothing short of apocalyptic. The radiation from such an event could strip away the Earth's protective atmosphere, exposing the planet's surface to dangerous levels of ultraviolet rays X-rays, and other high-energy radiation. This sudden influx of cosmic radiation could lead to a rapid shift in global climate patterns, potentially causing temperature spikes, atmospheric instability, and severe weather events. The consequences for life would be immediate and catastrophic. The delicate balance of ecosystems would be thrown into chaos, with many species unable to survive the sudden environmental changes. Given the rarity of gamma-ray bursts, the likelihood of one being directed at Earth is quite low, but it is still important to consider the possible scenarios and how we might mitigate the risks associated with such an event. Currently, our best line of defense against gamma-ray bursts comes from the realm of astronomy. By employing advanced telescopes and observational technologies, astronomers are able to monitor distant galaxies and track the signs of a potential gamma-ray burst. These tools can help scientists detect bursts long before they reach Earth, allowing us to assess the trajectory and potential impact of the burst. However, the challenge lies in the fact that gamma-ray bursts often originate from galaxies millions or even billions of light years away. The time it takes for the radiation from such an event to travel across vast distances means that any burst directed at Earth would not give us much time to react, reducing our ability to take immediate action. Yet, even though the immediate options for counteracting a gamma-ray burst are limited, that doesn't mean we should not prepare. One potential long-term strategy for mitigating the effects of a gamma-ray burst involves enhancing our understanding of atmospheric dynamics and boosting the overall health of Earth's atmosphere. While we cannot control cosmic events, bolstering the resilience of our atmosphere through global initiatives that address pollution, greenhouse gas emissions, and deforestation could help make the planet's protective layers more resilient. By slowing down the process of atmospheric degradation, we might give ourselves more time to respond to catastrophic events, whether they be from space or earthbound. Another avenue for improving resilience is through technological advancements in radiation shielding. The future of infrastructure might involve the construction of buildings and protective structures designed to withstand higher levels of radiation. These could incorporate specialized materials capable of absorbing or deflecting harmful rays, providing safe havens for human life in the event of extreme radiation levels. Furthermore, research into creating artificial magnetic fields, akin to the Earth's own magnetosphere, could provide an additional layer of protection against cosmic radiation, effectively creating a barrier that shields us from the harmful effects of gamma rays. While we currently lack the ability to counteract a gamma-ray burst directly, the key to survival in the face of such an event lies in preparation, adaptability, and resilience. Investing in education, awareness, and research into cosmic events is paramount. We must foster global cooperation to enhance monitoring systems and develop new technologies that can help us prepare for potential cosmic disasters. Sustainable practices that protect our environment and help maintain the health of the atmosphere are also crucial in improving our long-term resilience against radiation and other extraterrestrial threats. Black holes, another fascinating and terrifying aspect of the universe, share certain characteristics with gamma-ray bursts in that they are cosmic phenomena capable of altering the fabric of reality itself. Black holes originate from the life cycle of massive stars, which, after exhausting their nuclear fuel, can no longer support themselves against the immense force of gravity. This causes the core of the star to collapse inward, undergoing an extraordinary compression that leads to the formation of a singularity, an infinitely small point of infinite density. Surrounding this singularity is a boundary known as the event horizon, a point of no return. Beyond this boundary, the gravitational pull is so strong that not even light can escape. Anything that crosses the event horizon is lost forever, consumed by the black hole. What makes black holes so mysterious and terrifying is their combination of immense power and the unknowns surrounding their behavior. These cosmic giants can pull in everything from gas to entire stars, and even entire galaxies, consuming all material that strays too close. As matter spirals in toward the black hole, it heats up to unimaginably high temperatures, emitting energy across the entire electromagnetic spectrum. This process can often create dazzling displays of light, known as quasars, before the matter disappears completely into the black hole's depths. The raw energy and gravitational forces at play in a black hole's vicinity make it one of the most extreme and enigmatic phenomena in the universe, embodying the untamed power of the cosmos itself. The concept of a region in space where the known laws of physics seem to break down is a truly unsettling notion. It challenges everything we understand about the very fabric of reality and evokes a sense of unease. Such regions, often associated with black holes, present a cosmic enigma where time itself behaves differently. Near a black hole, the passage of time is distorted in ways that defy the conventional understanding of temporal progression, creating a reality in which our fundamental perceptions are thrown into disarray. These forces raise existential questions about the nature of the universe, about existence itself, and about the very nature of time and space. Are we truly in control of the universe around us, or are we merely participants in a grand cosmic game where the rules are constantly shifting and evolving? Black holes are not only fascinating objects of study, but they are also harbingers of the mysteries that lie at the heart of our universe. Perhaps they hold the key to some of the most profound questions about reality, questions that may even define the fate of time and space itself. If Earth were to be drawn into a black hole, the consequences would be nothing short of catastrophic. Initially, our planet would begin to experience the immense gravitational forces exerted by the black hole, forces that become progressively more intense as we draw closer to the singularity. This process, often referred to as spaghettification, would result in the stretching of Earth into an elongated, thin shape, akin to a cosmic string. The black hole's gravity would affect different parts of the planet with varying intensity, creating a stretching force that would ultimately tear the planet apart. In those final moments, our understanding of space and time would break down entirely. As Earth crosses the event horizon, the boundary beyond which nothing, not even light, can escape, the planet, along with everything on it, would be forever lost. No force could alter this fate. No force could reverse this cataclysmic pull. The distortion of time near a black hole is another unnerving aspect. Time would behave differently depending on the observer's position. A person on Earth might perceive time as passing normally, unaware of the impending doom. However, for an external observer, events would appear to slow down dramatically, almost coming to a halt as Earth drew closer to the event horizon. The closer the planet gets to the singularity, the more pronounced this time dilation effect becomes, ultimately resulting in a moment where time would seem to cease altogether. The tidal forces at play would also wreak havoc on Earth's structure, triggering catastrophic shifts in both the planet's physical integrity and its atmosphere. In those final moments, the very essence of life on Earth would be obliterated. The planet would cease to exist as we know it, swallowed whole by the black hole's insatiable gravitational maw. The fate of Earth would be sealed in a manner so absolute that nothing could reverse its tragic conclusion. The nearest known black hole to Earth lies in a star system known as V616 Monocerotis, or V6116 Mon. While this black hole is situated approximately 1,1600 light-years from Earth, an astronomical distance in itself, it remains far enough away that it poses no immediate threat to our solar system. To put the sheer scale of this distance into perspective, a light-year is the distance light travels in 1 year, roughly 5.88 trillion miles. Space is vast, and even this relatively close black hole is inconsequential in terms of its gravitational pull on our planet. The gravitational influence of a black hole, like that of any massive object, weakens as the distance from it increases. V616 Mon's location is such that its gravitational reach does not extend far enough to disrupt the orbits of planets in our solar system. In fact, black holes do not actively pull in matter from their surroundings, as often depicted in movies. Rather, they exert gravitational forces much like any other celestial body, such as a star or planet. It is only if a black hole were to come significantly closer to our solar system that its gravity would have any meaningful impact, potentially altering the orbits of planets or introducing disturbances into the solar system's delicate balance. In the grand scheme of things, the likelihood of a black hole making its way into our solar system is astronomically low. The universe is vast, and the distances between stars and their surrounding systems are mind-boggling. The cosmos operates on a scale so immense that the gravitational forces exerted by black holes are largely confined to the regions in their immediate vicinity. The nearest black hole's distance is so vast that its influence on Earth remains purely theoretical, a subject of scientific curiosity rather than immediate concern. One of the more fascinating phenomena in the universe are rogue planets, planets that drift through space without being bound to any star. These solitary wanderers roam the vast expanse of interstellar space, unanchored by the warmth and light of a sun. Their existence is a testament to the dynamic and often chaotic nature of planetary systems. Rogue planets are believed to be ejected from their original solar systems after undergoing complex gravitational interactions with other celestial bodies. A planet may be flung out of its host system through a powerful gravitational encounter with a massive neighbor, or as a result of destabilizing forces caused by multiple planets within the same system. Once cast out, a rogue planet is free to travel across the universe for billions of years, untethered to any star and without the warmth or light that most planets rely on for survival. These rogue planets, often dark and cold, become frozen relics of their former homes. Their temperatures plummet to levels so low that they remain in a state of deep freeze. In some cases, however, rogue planets may still retain residual heat from their initial formation, providing a faint, lingering trace of the energy they once possessed. The existence of rogue planets raises intriguing questions about the potential for life in the universe. Could these isolated worlds harbor conditions that support life, or must they always remain barren, uninhabitable wastelands? As astronomers continue to discover more of these rogue planets, we gain new insights into the processes of planetary formation and the potential for life in the universe. These discoveries deepen our understanding of the complexities that define the cosmic order. When a rogue planet drifts into our solar system, it can cause significant disruptions to the celestial mechanics that govern the orbits of the planets. Imagine our solar system as a finely tuned orchestra, with each planet playing its part in harmony. The sudden arrival of a rogue planet is akin to a disruptive conductor, one who dramatically alters the symphony of planetary motion. As the rogue planet approaches, its gravitational pull begins to influence the orbits of nearby planets. Depending on the size and mass of the rogue planet, it could either draw other planets closer or push them further away from the sun. These changes in gravitational dynamics can have far-reaching consequences, not just for the planet directly affected, but for the entire solar system. For instance, a previously stable orbit might become more elliptical and chaotic, leading to unpredictable changes in the climate on Earth. This could range from drastic temperature fluctuations to a destabilization of the planet's atmosphere. In the worst case, a rogue planet could bring with it the risk of potential collisions, as the new gravitational forces alter the paths of other celestial bodies. The asteroid belt, situated between Mars and Jupiter, might be disturbed by the rogue planet's gravity, sending asteroid fragments hurtling toward the inner solar system. The risk of impacts on Earth and other inner planets would rise dramatically, introducing new dangers to our fragile existence. This kind of chaos would transform our solar system from a relatively stable and predictable environment into a chaotic and uncertain one. The presence of a rogue planet in the solar system would represent more than just a disruption. It would be a game changer. The effects of its arrival would reverberate across the solar system, reshaping the orbits of planets and creating a new cosmic order. The consequences of such an event could be anything from minor orbital adjustments to full-scale collisions, highlighting the fragile nature of our solar system and the vulnerability of the delicate balance that governs it. Detecting rogue planets presents unique challenges, primarily due to their elusive nature. Unlike planets that orbit stars, which emit light and are relatively easy to spot through telescopes, rogue planets do not shine brightly on their own. Without a nearby star to illuminate them, they are difficult to detect through traditional methods. They do not reflect much light, making it nearly impossible to observe them with the naked eye. Instead, rogue planets are often detected through their faint heat signatures. These heat signatures, however, are incredibly difficult to capture, requiring highly sensitive infrared technology to pick up on the faint radiation they emit. The vastness of space presents another major hurdle in the search for rogue planets. The distances between stars and planetary systems are so immense that the likelihood of a rogue planet passing close enough to be detected by our instruments is relatively low. Moreover, rogue planets are often hidden from view by cosmic dust, gas, or other celestial bodies that obscure our observation tools. Even when infrared technology is used to detect these faint signals, the sensitivity required to identify a rogue planet from such vast distances is immense. The field of view for most telescopes is limited, and rogue planets which drift between stars may not always be within the range of these instruments. Even when they do pass close enough, the window of opportunity to detect them can be incredibly brief. There is also the challenge of distinguishing rogue planets from other celestial phenomena. Many objects in space share similar characteristics, such as emitting heat or moving in ways that resemble a planet's trajectory. This makes it difficult to distinguish rogue planets from other cosmic objects like asteroids, brown dwarfs, or even small stars. To address this issue, scientists have had to develop sophisticated algorithms and methodologies to differentiate between rogue planets and other objects. By refining these detection techniques, astronomers hope to unlock more secrets of the universe and improve our understanding of these mysterious, solitary wanderers that roam the cosmos. In the vastness of the universe, certain celestial phenomena stand out, not just for their awe-inspiring nature, but also for their rarity. One such occurrence is the rogue planet, an elusive wanderer that does not orbit any star, instead drifting through the cosmic void, untethered by the gravitational pull of a central star. The rarity of these planets adds a layer of mystery and intrigue, as the chances of encountering one are relatively low compared to the sheer number of stars scattered across the galaxy. This scarcity, combined with the challenges of their detection, makes studying rogue planets an incredibly difficult task for astronomers. Their very nature, devoid of the light typically associated with other planets, combined with the expansive and chaotic environment of space, contributes to the challenge. With so many other celestial bodies filling the same stretch of the universe, the search for rogue planets remains a monumental task for scientists. In a universe as dynamic as ours, cosmic collisions happen frequently, some barely noticeable, while others are earth-shattering in their intensity. These collisions can involve a variety of celestial bodies, from smaller objects like asteroids and comets, to massive stars and even entire galaxies. The impacts that result from the interaction of these objects are not always catastrophic, but they can reshape planets, alter landscapes, and have long-term consequences on the environment. Perhaps the most common collisions are those between smaller celestial bodies, asteroids and comets. While many of these impacts are minor, occasionally their effects can be far-reaching, especially if the object in question is large enough to cause significant damage. When such an object strikes a planet like Earth, it has the potential to drastically alter the planet's surface, sometimes leading to catastrophic events such as mass extinctions. These collisions, while seemingly random, are a constant reminder of the volatile nature of our solar system. However, the danger escalates when stars collide. These cosmic behemoths, drawn toward one another by the pull of gravity, can engage in a deadly dance that results in one star consuming the other. Such collisions can give rise to exotic and dense remnants such as neutron stars or even black holes. The energy released in these cataclysmic events is beyond comprehension, with radiation being emitted in massive quantities, affecting the surrounding space and the stars within its reach. The repercussions are immense, with entire star systems being altered or even destroyed in the process. On a larger scale, galaxies themselves can collide. The process is slower compared to individual stellar collisions, but the complexity is no less daunting. When two galaxies merge, their stars and gas clouds interact in violent, chaotic ways. These interactions can trigger the birth of new stars, as well as explosive events that shake the very fabric of the galaxies involved. Stars within these galaxies can be ejected into intergalactic space, while others may undergo intense bursts of star formation that destabilize nearby systems. The potential consequences are vast, affecting not just the immediate galaxies, but also the space surrounding them. Among the most dangerous of all cosmic collisions are those involving black holes. When two black holes spiral toward one another, their eventual merger sends shockwaves through space, creating ripples in spacetime known as gravitational waves. These waves carry an immense amount of energy, and the event itself can glow across different electromagnetic spectrums, allowing scientists to detect the merger from vast distances. The forces at play in such collisions not only disrupt the cosmic environment around the black holes, but they can also create significant repercussions for any celestial bodies that happen to be nearby. These violent events are a stark reminder of the dynamic, ever-changing nature of the universe, a constant state of flux where even the most stable systems can be upended in an instant. As we gaze out into the infinite expanse of space, it becomes clear that these cosmic collisions are an inevitable aspect of the universe. Yet, it is the collision of black holes and dense stars that represents the ultimate expression of danger, with the potential to disturb the very fabric of space itself. These collisions can affect entire star systems, sending ripples through space that extend across light years, leaving lasting impacts on the cosmic environment. While these cosmic events can seem like abstract, distant phenomena, they have the potential to affect us here on Earth. As we contemplate the possibility of an interstellar collision involving our own planet, it becomes apparent that the prediction and prevention of such events is a complex endeavor requiring a deep understanding of celestial mechanics. By observing the intricate dance of objects in our galaxy, scientists can track the movements of asteroids, comets, and other celestial bodies, anticipating potential collisions long before they occur. The process of predicting a potential interstellar collision with Earth begins with the observation of the vast number of celestial objects that populate our galaxy. These objects, from the tiniest asteroid to massive comets, move in defined orbits, and by tracking their positions over time, astronomers can build a picture of where they are headed. Advanced telescopes and radar systems play a crucial role in this process, providing the data necessary to predict the trajectory of these objects with incredible accuracy. When a threat is detected, meaning that the orbit of an object intersects with that of Earth's, scientists begin to calculate its future path, factoring in the gravitational influences of other celestial bodies. Once a potential threat is identified, the next step is to determine how to mitigate the risk. Over the years, various strategies have been proposed to avert a collision with a large celestial body. One of the most discussed methods involves the use of kinetic impactors, large spacecraft designed to collide with the threatening object. The idea is simple. By imparting a small amount of force upon the object, the spacecraft would change its trajectory, nudging it off course enough to avoid a collision with Earth. While this method is straightforward in concept, it would require significant precision and coordination. Another method involves the use of gravity tractors. These are spacecraft that would fly alongside the rogue object, using their own gravitational pull to gradually change its course. This method is less aggressive than a kinetic impactor and would take longer to have an effect, but it carries less risk of creating debris that could pose additional hazards to the planet. The slow, gentle pull of a gravity tractor could potentially nudge an object into a safer orbit, diverting it from a collision course with Earth. In more urgent scenarios where time is of the essence, more drastic measures may need to be considered. Some scientists have proposed the use of nuclear devices to disrupt a threatening object. By detonating a nuclear device near the object, the resulting explosion would vaporize parts of the celestial body, creating a force strong enough to change its trajectory. While this method might seem like a last resort, it carries significant risks. The explosion could break the object into smaller fragments, and those fragments could still pose a threat to Earth. Furthermore, the environmental consequences of such an explosion, including fallout and debris, would need to be carefully considered. As our observational technologies improve and our understanding of celestial bodies grows, our ability to predict and, if necessary, prevent catastrophic interstellar collisions will continue to advance. However, this will require global cooperation and the sharing of data across borders. No single nation can face these threats alone, and working together will be essential in safeguarding our planet from potential cosmic dangers. Throughout Earth's history, the evidence of past cosmic collisions has been embedded in the planet's geological record. One of the most compelling pieces of evidence lies in the numerous impact craters scattered across the globe. These craters, formed by asteroids and comets crashing into Earth, vary greatly in size and age, providing a timeline of the many cosmic bombardments the planet has endured. Perhaps the most famous of these craters is the Chicxulub crater in Mexico, which was formed by a massive impact approximately 66 million years ago. This event is widely believed to have contributed to the mass extinction that wiped out the dinosaurs, marking a significant turning point in the history of life on Earth. In addition to craters, scientists also study layers of sediment that contain specific minerals and chemical signatures, which are indicative of extraterrestrial impacts. For example, a layer of iridium, a metal that is rare on Earth but more common in asteroids, has been identified in sediments from around the time of the dinosaur extinction. This iridium anomaly serves as a key marker for a significant extraterrestrial event, further supporting the theory that a cosmic collision played a pivotal role in the extinction event. Beyond physical scars and chemical traces, scientists also analyze the geological patterns associated with ancient impacts. These patterns can include shock metamorphism, which occurs when the extreme pressure from an impact alters the structure of rocks, creating unique microstructures in minerals that can only form under the intense conditions produced by a cosmic collision. While asteroid impacts are more commonly discussed, comets, icy bodies that develop glowing comas and tails as they approach the sun, can also have significant effects on planets. Although cometary impacts are less frequent, they can still cause immense damage when they do occur. Earth experiences impacts from comets approximately once every few centuries, though the majority of these are smaller objects that cause only localized damage. Larger comets, on the other hand, can have catastrophic effects, releasing energy equivalent to millions of tons of TNT, potentially leading to widespread destruction. The famous impact event believed to have contributed to the extinction of the dinosaurs is often attributed to a comet or asteroid striking the Earth, unleashing devastating effects that forever altered the climate and ecosystems of the planet. Space agencies around the world continue to monitor nearby comets and other near-Earth objects in order to assess any potential threats. Though the chances of a catastrophic comet impact remain low on a human timescale, the history of Earth serves as a constant reminder that such events, though rare, do occur. The dynamic nature of our planet's history, coupled with its interaction with the cosmos, underscores the importance of vigilant monitoring. Preventing a catastrophic cometary impact requires a multifaceted approach, combining advanced technology, observation, and international collaboration. Astronomers constantly scan the skies for near-Earth objects, tracking their movement and assessing their potential threat. Early detection is crucial as it provides the time needed to develop a strategy to prevent or mitigate an impact. If a potential threat is identified, the object's trajectory is calculated and analyzed. If the object poses a risk to Earth, various strategies can be employed to deflect or destroy it. These strategies may include the use of kinetic impactors, gravity tractors, or, in extreme cases, nuclear devices. By studying the skies and improving our ability to predict and respond to cosmic threats, we can better prepare for potential collisions in the future, safeguarding our planet against the forces of the universe. International collaborations have become an essential part of our efforts to understand and mitigate the potential threats posed by celestial bodies like comets. Agencies such as NASA, National Aeronautics and Space Administration, ESA, European Space Agency, and a multitude of global organizations have pooled together their knowledge, resources, and technology to share information and develop better strategies for monitoring, predicting, and responding to these cosmic threats. By working together across borders, these collaborations enhance the collective scientific capabilities, ensuring that the world is better equipped to face any possible dangers from outer space. Such partnerships allow for the formation of a global network that is always on alert, prepared for the possibility that a comet may one day be detected on a collision course with Earth. The creation of such a global network has significant benefits, as it ensures that if a comet is detected, There are pre-existing, well-developed plans ready to mobilize. These plans include coordinated actions from the scientific community, which involves astronomers, physicists, and engineers working together to respond effectively. By sharing data and knowledge from different countries, scientists can work in unison, ensuring that their response is timely and effective, and that no important detail is overlooked. The response would be based on detailed observations of the comet's trajectory, speed, and composition, allowing experts to craft precise plans for deflection or mitigation. This ability to act swiftly and collaboratively increases the likelihood of averting a disaster. However, beyond just having a network in place for immediate response, continued research into comets' behaviors and materials is crucial. The more we understand about these icy wanderers, the better equipped we will be to prevent or deflect them in the future. For instance, examining the composition of comets, their chemical makeup, structure, and the way they interact with the solar wind can provide scientists with valuable insights into the best methods for intervening should a threat arise. Understanding the materials within comets, such as frozen gases, dust, and organic compounds, is critical because it allows for the refinement of technologies designed to alter their paths or destroy them in a controlled manner. This research has the potential to lead to breakthroughs in space engineering and planetary defense, improving the chances of successful interventions if ever a real threat emerges. This combination of monitoring, technological innovation, and international unity forms the backbone of a robust defense system against the potential dangers posed by comets. As we continue to study and understand comets, we become more adept at responding to their unpredictability and minimizing their risks. After all, comets are not just fascinating celestial objects. They are symbols of the dynamic and often perilous nature of our universe. Their erratic journeys through space serve as constant reminders that Earth is part of a much larger cosmic system, where events far beyond our control can have significant consequences for our planet's survival. Comets themselves are among the most awe-inspiring of celestial phenomena, offering us a glimpse into the earliest days of our solar system and, by extension, the formation of our universe. These icy bodies, which are composed primarily of dust, rock, and frozen gases, originate from some of the most distant reaches of our solar system, the Kuiper Belt and the Oort cloud. These regions, far beyond the orbit of Neptune, are home to many of the solar system's most primitive and volatile objects. As a comet approaches the sun, the heat causes its icy materials to vaporize, creating a glowing coma, the head, and a spectacular tail. This tail, which can stretch for millions of kilometers, is one of the most iconic features of comets, a visual marvel that can often be seen with the naked eye. However, the transformation of a comet as it nears the sun is not merely a visual phenomenon. It marks a crucial interaction between the comet and the solar system. The volatile materials that make up the comet react to the sun's radiation, releasing gases and dust that form the comet's signature tail. These interactions provide scientists with critical data about the composition of comets and their behavior, helping to refine our understanding of how the solar system was formed and how it continues to evolve. In many ways, comets are like time capsules, preserving ancient materials that date back to the early solar system. By studying them, we can gain insights into the processes that shaped not only our own planet, but also the conditions that might have allowed life to emerge. Comets are often referred to as dirty snowballs, due to their combination of frozen water, dust, and rock. As they travel through the solar system, they shed debris in their wake. This debris can influence planetary atmospheres, sometimes creating meteor showers when Earth passes through the remnants of a comet. These showers, which occur at regular intervals, serve as a reminder that our planet is constantly affected by the cosmic dust that drifts through space. When Earth intersects the debris trail left behind by a comet, tiny fragments of rock and ice collide with the Earth's atmosphere, creating the dazzling streaks of light we call meteors. But the significance of comets goes beyond their role in meteor showers. They also hold clues about the origins of life itself. Many scientists believe that comets may have played a pivotal role in delivering the essential ingredients for life to early Earth. These icy bodies are thought to contain organic compounds, amino acids, and even water. all of which are critical for the development of life. Some researchers speculate that it was the arrival of these materials, either via comet impacts or through other cosmic mechanisms, that sparked the biochemical processes that led to the emergence of life on Earth. On the other hand, the impact of a comet can also have catastrophic consequences. History has shown us that celestial objects such as comets and asteroids have had a profound impact on Earth's biological evolution. One of the most famous examples is the theory that a large comet or asteroid impact contributed to the mass extinction event that wiped out the dinosaurs about 65 million years ago. This illustrates the dual nature of comets. They are not only carriers of life's building blocks, but also potential destroyers of civilizations. These events can dramatically alter the course of life on a planet, as evidenced by the sudden shifts in climate and ecosystems that often follow such impacts. Understanding comets and their potential for destruction is just as important as studying their role in the origins of life. In this way, comets serve as both creators and destroyers. They offer a window into the formation of our solar system and enhance our understanding of biological evolution, but they also remind us of the dynamic and unpredictable nature of the cosmos. Comets are like messengers from the early days of our universe, holding within them the secrets of how everything began and how the universe continues to evolve. Their unpredictable paths through the solar system, their close encounters with planets, and their potential to either nurture or destroy all serve to emphasize the fragility of life on Earth and the need for continuous vigilance in the face of the vastness of space. Turning our attention to another intriguing phenomenon in the universe, magnetars are a class of neutron stars that possess magnetic fields of incredible strength, far beyond anything we can imagine. In fact, the magnetic fields of magnetars are 1,000 trillion times stronger than those found on Earth. To understand just how powerful this is, imagine the magnet on your refrigerator, but scaled up to an unimaginable degree. These fields are not only incredibly strong, but they are also complex and highly dynamic, often twisting and spiraling in intricate patterns that are still not fully understood. This complexity plays a central role in the behavior of magnetars, particularly in the violent outbursts of energy that they can produce. When a magnetar's magnetic field lines become so tightly twisted that they can no longer maintain their structural integrity, they snap, releasing enormous amounts of energy. This release of energy is what triggers the cosmic flares that are characteristic of magnetars. These flares, though brief, are incredibly intense and release an enormous amount of radiation, often in the form of X-rays and gamma rays. The energy produced during such an event is staggering, equivalent to the combined energy output of millions of suns, all released in just a few seconds. This burst of energy can send shockwaves through space, potentially affecting nearby celestial bodies and influencing the cosmic environment around the magnetar. The impact of a magnetar flare on its surroundings can be profound. The intense magnetic field can alter the behavior of cosmic dust and gas, and the radiation can affect any nearby stars, planets, or even the fabric of space itself. If a magnetar flare were to be directed towards Earth, the effects could be devastating. The radiation emitted could potentially disrupt electronic systems, cause damage to satellites in orbit, and pose risks to astronauts who are traveling through space. Even the Earth's upper atmosphere might be altered by the intense radiation, which could have consequences for life on the planet. Fortunately, magnetars are located millions of light years away from Earth, so the likelihood of a flare affecting our planet is extremely low. However, the potential consequences of such an event have made it a focus of astronomical study. By monitoring magnetars and understanding their behavior, scientists hope to better predict and prepare for the potential risks associated with these stellar phenomena. While the threat remains distant, the study of magnetars contributes to our broader understanding of stellar evolution, magnetic fields, and the extreme physics that govern the behavior of some of the most powerful objects in the universe. Recent technological advancements have significantly enhanced our ability to study these rare and often elusive cosmic phenomena. The development of more advanced telescopes has allowed astronomers to capture sharper, more detailed images of distant objects, such as galaxies, black holes, and supernovae. These improved imaging technologies are crucial for studying the intricate features of these distant phenomena and understanding their underlying physical properties. Additionally, the field of radio astronomy has opened up new possibilities for observing the universe. By using radio telescopes, scientists can detect signals from objects that are invisible to optical telescopes, such as pulsars and quasars. These signals provide crucial information about the structure and dynamics of our universe, helping to paint a more complete picture of how the cosmos functions. Spectroscopy, another key tool in modern astronomy, has also seen significant advancements. By analyzing the light emitted or absorbed by celestial objects, scientists can determine crucial details about their composition, temperature, motion, and even their internal structure. This information is vital for understanding the life cycles of stars, the formation of galaxies, and the chemical evolution of the universe. The combined use of these advanced techniques allows astronomers to probe the depths of space in ways that were once unimaginable, unlocking new mysteries and expanding our understanding of the cosmos. Furthermore, space-based observatories have taken our ability to observe the cosmos to extraordinary new heights. By placing scientific instruments above Earth's atmosphere, an atmospheric layer that often distorts and scatters light, astronomers gain unprecedented clarity and range. Instruments like the Hubble Space Telescope, positioned far beyond the interference of the atmosphere, allow scientists to peer deeper into the universe than ever before. This strategic placement makes it possible to observe objects that are billions of light years away, providing invaluable insights into the early stages of the universe. This unprecedented access enables astronomers to study distant galaxies, nebulae, and stellar phenomena with a level of precision and detail that was once beyond imagination. Moreover, advancements in computational power have revolutionized how data is processed and analyzed. What once required immense manual effort and time-consuming methods can now be achieved with remarkable efficiency through complex simulations and sophisticated models. These computational breakthroughs allow researchers to simulate astronomical events, from the birth of stars to the collision of galaxies, with a degree of accuracy that enables them to predict outcomes based on current observations. This marriage of observational data and theoretical models is essential for constructing a more comprehensive and accurate picture of cosmic phenomena. The power to run vast simulations and analyze enormous data sets at unprecedented pace has opened the door to new possibilities in space research, enabling scientists to delve into the mysteries of the universe with tools that were once the stuff of science fiction. The synergy between these technological advances creates a rich and powerful toolkit for modern researchers. By utilizing space-based observatories in combination with powerful computational models, scientists now have the means to investigate the vastness of space and its complex phenomena with an efficiency that would have been inconceivable just a few decades ago. The insights gained from this wealth of data are reshaping our understanding of space and unlocking mysteries that were once hidden far beyond our reach. One of the most intriguing aspects of modern astrophysical research involves cosmic rays. These high-energy particles, which travel at nearly the speed of light, originate from deep space. They are primarily composed of atomic nuclei, with protons being the most abundant, though they also include heavier elements and even electrons. The sources of these cosmic rays are varied, with the most powerful bursts often emanating from phenomena such as supernova explosions, active galactic nuclei, and even our very own sun. As these energetic particles journey across vast distances, they become a fascinating tool for studying the universe. When cosmic rays approach Earth, they interact with the atmosphere in a dramatic and often complex way. Upon entering the Earth's atmosphere, these high-energy particles collide with molecules of air, such as nitrogen and oxygen. This interaction sets off a cascade of secondary particles, much like a chain reaction. Essentially, one cosmic ray can trigger the creation of many additional particles, including muons, electrons, and gamma rays. Some of these particles continue their descent, reaching Earth's surface, where they can be detected and studied by specialized instruments. Cosmic rays play an important and multifaceted role in both the environment of Earth and our understanding of the universe. One of the most striking effects of cosmic rays is their ability to cause ionization in Earth's atmosphere, a process that can influence weather patterns and even contribute to the formation of clouds. This interaction with the atmosphere also plays a role in atmospheric chemistry and is central to our understanding of the Earth's environment. While most cosmic rays do not pose a direct threat to life on Earth, they can still have profound effects on technology and human health, especially in the context of space exploration and high-altitude flight. For astronauts and high-altitude flight crews, cosmic rays represent a significant health risk. While Earth's atmosphere provides substantial protection from these energetic particles, there are still occasions when cosmic rays make it through, particularly during periods of heightened solar activity. Prolonged exposure to these particles can cause damage to human cells, potentially leading to mutations in DNA. If these mutations are not properly repaired, they can develop into cancers over time. This heightened risk of cancer is a serious concern for astronauts embarking on long-duration missions in space, where the protective atmosphere of Earth is no longer present. The effects of cosmic rays also extend to technology, where these high-energy particles can disrupt electronic systems. Satellites, in particular, are especially vulnerable to cosmic rays. These particles can strike delicate components of spacecraft, such as the memory chips in satellites, causing data corruption or system failures. This is particularly critical given the role that satellites play in global communication, weather forecasting, navigation systems, and a multitude of other functions that are integral to modern life on Earth. The disruption of these systems could have wide-reaching effects on both daily life and scientific progress. As we continue to rely on technology that operates in space, understanding the impact of cosmic rays on these systems is becoming increasingly important. In light of these risks, scientists are actively exploring strategies to mitigate the effects of cosmic rays, especially for future space missions. One approach involves enhancing shielding on spacecraft to better protect astronauts and delicate equipment from cosmic radiation. Engineers are testing various materials that can absorb or deflect these particles, reducing their impact. Research in this area is focused on developing more effective materials and structures that can offer better protection during long-duration missions, especially those beyond Earth's orbit. Another key strategy involves adjusting the operational schedules of space missions. Researchers are looking into the possibility of timing spacecraft activities to coincide with periods of low cosmic ray activity. By closely monitoring solar activity and understanding the correlation between solar flares and cosmic ray intensity, scientists can predict times when cosmic rays will be less likely to reach Earth or affect spacecraft. This predictive modeling allows astronauts to take precautionary measures during periods of heightened cosmic ray exposure, such as sheltering in more shielded areas of the spacecraft or altering mission timelines to avoid high-risk periods. In addition to shielding and timing, scientists are also working on developing more accurate models to predict cosmic ray exposure. By integrating data from satellites, telescopes, and ground-based observatories, researchers are developing sophisticated forecasting systems that can predict cosmic radiation levels with greater accuracy. This knowledge could be crucial for planning future space missions, allowing astronauts to avoid the worst of cosmic ray storms or to adjust their schedules to mitigate exposure. While Earth's atmosphere offers a significant layer of protection, the exploration of space beyond our planet requires careful consideration of the dangers posed by cosmic rays. As humanity prepares for missions to the Moon, Mars, and beyond, the ability to predict and shield against these high-energy particles will be essential. Understanding the full extent of the cosmic ray threat is vital, not only for the safety of astronauts, but also for the protection of the technologies that will make future space exploration possible. This evolving research is crucial as we look to the future, ensuring that we are prepared for the challenges of deep space exploration while continuing to unlock the secrets of the universe. As humanity continues to look toward the stars, researchers are diving deeper into understanding the biological protective measures that could safeguard the human body against the growing concern of increased radiation exposure. The risks posed by radiation in space are significant given the vast and unpredictable nature of cosmic environments, and there is an urgent need to explore solutions that can help mitigate these dangers. Among the most promising avenues being explored are medicinal approaches, including specific diets, supplements, and perhaps even genetically tailored solutions that could bolster human resilience to space radiation. This burgeoning field of study, though still in its early stages, is part of a broader quest to ensure that as we venture into the unknown expanses of space, we are not only prepared technologically and psychologically, but biologically as well. The ultimate goal is to ensure that humanity's reach for the stars is not impeded by the fundamental dangers of the universe's most energetic and unpredictable phenomena. In this larger context, it is important to recognize that space is not just a vacuum waiting to be explored. It is filled with immense, often hostile forces that can shape the future of our species. The universe, in its vastness, holds many mysteries, and one of the most fascinating phenomena that has captured the attention of astronomers and astrophysicists is galactic cannibalism, a cosmic process that is as violent as it is intriguing. In simple terms, galactic cannibalism refers to the event in which a larger galaxy absorbs a smaller one. Imagine two colossal galaxies drifting in space like enormous celestial ships, each with their own distinct structure, but destined to collide. As they move closer, the gravitational forces between them begin to interact, and what follows is nothing short of a galactic drama. When these gravitational forces come into play, they begin to stretch and distort the shapes of each galaxy. The larger galaxy typically exerts a stronger pull, overpowering the smaller one. Over time, this immense gravitational force draws in stars, gas, and even dark matter from the smaller galaxy, essentially consuming it. The process is not quick or simple. It unfolds over billions of years, with the smaller galaxy gradually merging into the larger one. During this lengthy transformation, fascinating changes occur. New stars may form from the gases drawn together, and the overall structure of the larger galaxy evolves, becoming more complex and rich in features. This form of galactic evolution plays a crucial role in the growth of galaxies, shaping their structure and their future in ways that we are only beginning to understand. Galactic cannibalism is not an anomaly, but rather a key ingredient in the ongoing cosmic dance that governs the universe. The merger of galaxies, which often involves the absorption of smaller ones, is a reminder of the ever-changing nature of the cosmos, where celestial bodies are constantly colliding, interacting, and transforming. These interactions are not merely destructive, but give birth to new formations, ultimately resulting in the evolution of new galactic structures. Looking at our own Milky Way galaxy, we find that it has experienced multiple episodes of galactic cannibalism in its own history. A prime example is the ongoing interaction between the Milky Way and the Sagittarius dwarf spheroidal galaxy. Sagittarius, once an independent galaxy, has entered the gravitational influence of the Milky Way and is slowly being drawn into its larger gravitational embrace. As this process unfolds, the shape of both galaxies is being distorted, with the Milky Way's greater mass overwhelming Sagittarius. This slow-motion collision is a perfect example of how smaller galaxies are gradually consumed by larger ones, as the Milky Way continues to evolve and grow. In another striking example, the Andromeda Galaxy, our closest spiral neighbor, is on a collision course with the Triangulum Galaxy. Triangulum, though smaller than Andromeda, is still significant in size and will be drawn into the larger galaxy during this cataclysmic event. As Andromeda absorbs the Triangulum Galaxy, the event will not only alter its structure, but will likely lead to dramatic changes in the processes that govern star formation within the galaxy. This impending merger highlights just how dynamic the cosmos truly is, and how even the largest structures in the universe are subject to the forces of galactic cannibalism. The antennae galaxies known as NGC 4038 and NGC 4039 offer a breathtaking example of galactic cannibalism in action. These two spiral galaxies are currently merging in a dramatic cosmic dance. As they draw closer, tidal forces between them pull gas and stars from one another, creating waves of star formation. The immense gravitational pull at work in this interaction triggers the birth of new stars, giving the entire event a rejuvenating quality. These stars, born out of the chaos of galactic cannibalism, become a symbol of how galaxies can, in some sense, be reborn through these dramatic mergers. The antennae galaxies stand as a testament to the incredible transformations that occur during such mergers. Through this process, galaxies not only evolve but also change their entire structure, and in some cases, they even begin to reshape the very fabric of their surrounding cosmic environment. As galaxies collide and merge, they leave an indelible mark on the entire cosmic landscape, influencing everything from star formation to the ultimate fate of the galaxy itself. In the grand narrative of the universe, the Milky Way's fate is intricately tied to these cosmic phenomena. As we gaze at the future, there is the very real possibility that we too will witness a galactic cannibalism event. While the exact timeline is still a mystery, the prospect of the Milky Way colliding with the Andromeda Galaxy in roughly 4 billion years is an exciting, albeit distant, chapter in the story of our galaxy. This colossal merger will be a slow, gradual process, with both galaxies' gravitational pulls drawing them ever closer until they inevitably collide. During this event, it is likely that the smaller galaxies involved will lose their individual identities, becoming part of the larger, more powerful galaxy. The process of galactic cannibalism will reshape not just the structure of the galaxies involved, but also the stars within them. As these galaxies merge, the stars within them will be redistributed, forming new patterns and creating new galactic systems. For the Milky Way, this will represent yet another step in its own ongoing evolution. At the heart of this process lies a deeper truth about the universe, that galaxies are constantly in motion, evolving and adapting in response to the dynamic forces at play in space. The Milky Way has already shown signs of this galactic cannibalistic behavior, having previously consumed several dwarf galaxies that ventured too close. These swallowed galaxies have left traces in the form of stars and other remnants scattered across the Milky Way, highlighting the enduring impact of such cosmic events. While we are not yet facing this merger in our lifetime, the potential for it to occur is a testament to the incredible scale and complexity of the universe. It also serves as a reminder that, in the grand scheme of things, humanity is just one small part of a much larger cosmic ballet, a dance in which galaxies, stars, and even entire civilizations are caught up in an eternal cycle of birth, transformations, and eventual dissolution. As we turn our gaze inward and examine the stellar nurseries scattered across the universe, we encounter another fascinating phenomenon. Stellar nurseries are vast clouds of gas and dust, often found in regions known as molecular clouds, where the birth of new stars occurs. These nurseries are critical to the life cycle of stars, and their evolution is intimately connected to the overall growth and structure of galaxies. Within these nurseries, gravity plays a crucial role, pulling together particles and initiating the processes that ultimately lead to the formation of new stars. These stellar nurseries can be thought of as cosmic cradles, where the raw materials of the universe are gathered and shaped into new celestial bodies. However, not everything within these nurseries unfolds smoothly. Several factors can disrupt the delicate balance needed for stable star formation, potentially leading to chaos within the cloud. For example, supernova explosions from nearby stars can send shockwaves through the cloud, heating it up and causing the material to disperse. This disruption can halt star formation, prevent new stars from forming, or even tear apart the existing structures within the nursery. Gravitational forces within the nursery can also lead to fragmentation. Some regions within the cloud might compress enough to form stars, while others may be torn apart before they can stabilize. This uneven process creates a dynamic and often chaotic environment where gas and dust swirl unpredictably, making it difficult to maintain stability and structure. The rapid formation of too many stars within a short period can also lead to problems. As these young stars form, they emit powerful stellar winds and radiation, creating a highly energetic environment that can push surrounding gas and dust away, further complicating the conditions necessary for continued star formation. This creates a feedback loop, where the very forces that give birth to stars also shape the evolution of the surrounding environment in dramatic and unpredictable ways. Stellar nurseries, despite these challenges, remain essential to the birth and evolution of stars, and by extension, galaxies. They are the engines that fuel the ongoing transformation of the universe, and the processes that occur within them can have profound effects on the overall structure and stability of the galaxies they inhabit. The birth of stars, in all its tumultuous glory, is a defining feature of the universe, a reminder that even in the darkest corners of space, new life is always waiting to emerge. When massive stars reach the final stages of their life cycles, they often end in spectacular explosions known as supernovae. These cataclysmic events release an enormous amount of energy, scattering elements across space in a fiery ballet of destruction and creation. The immense power of a supernova doesn't just mark the end of a star, it forever alters the dynamics of the surrounding cosmic region. As the star explodes, it sends shockwaves through the interstellar medium, adding turbulence and shifting the entire environment. This scattering doesn't only enrich the universe with heavier elements, but it also stirs and mixes the surrounding gas and dust, creating a cosmic storm of activity that accelerates the processes of star and planetary formation. This energy release, the result of a star's life and death, ignites a chain reaction, a cycle of creation and destruction that plays an essential role in the evolution of galaxies. Every explosion adds to the mixture of gases that will eventually give birth to new stars. It's a process that shapes the very fabric of the universe itself, continuously weaving new threads into the vast cosmic tapestry. This intricate cycle, filled with chaotic movements and transformations, fuels the cosmic machinery that dictates the future of galaxies, stars, and planetary systems, influencing everything from the formation of distant star systems to the intricate conditions required for life itself. At the heart of this cosmic dance are stellar nurseries, regions of space where new stars are born. These nurseries, often referred to as nebulae, are breathtaking sights in the universe. Vast clouds of gas and dust swirling together in complex patterns. Within these clouds, the forces of gravity begin to assert their dominance, pulling particles together in a dense, compact region. As this gas and dust accumulate, they form a core that grows increasingly dense and hot, leading to the birth of a protostar. A protostar is essentially a young star on the cusp of ignition, one that has not yet begun nuclear fusion. The intense gravitational forces compress the material so tightly that the protostar becomes a beacon of infrared light, a glowing ember in the darkness of space. One of the most fascinating aspects of stellar nurseries is the dramatic formation of protostars. As the gas and dust accumulate, the increasing pressure and temperature force particles to collide, releasing enormous amounts of energy. This process not only fuels the growth of the protostar, but also contributes to the overall dynamics of the stellar nursery. The surrounding gas and dust aren't static. They are constantly being stirred, heated, and compressed by the forces at play. These processes create a tumultuous environment filled with violent interactions. Jets of gas are often ejected from the young protostar, which can travel vast distances and impact the surrounding material. These jets, which shoot along the star's rotational axis, are highly energetic, and their impact on the surrounding gas creates shockwaves that trigger the formation of even more stars. It's as if the nursery is constantly giving birth to new stars in a cascading sequence, each one emerging from the swirling chaos of the gas clouds. Within these stellar nurseries, astronomers have observed an incredible variety of chemical compounds. The complexity of these compounds, ranging from simple molecules like water and carbon dioxide to more intricate organic compounds, has led scientists to rethink the origins of life. Some of the fundamental building blocks of life on Earth, such as amino acids and other complex molecules, may have originated in these cosmic clouds. The chemical reactions taking place within these nurseries are like a cosmic laboratory, providing clues about how life might have emerged in the universe. The study of stellar nurseries reveals yet another layer of cosmic complexity. These regions are not merely the birthplaces of stars, but they are also laboratories for understanding the fundamental processes that govern the universe. The bright, vivid colors of images captured by astronomers are more than just aesthetically pleasing. They are key to unraveling the mysteries of the cosmos. Different gases emit light at specific wavelengths, and by studying the colors emitted from these nebulae, astronomers can deduce the composition, temperature, and density of the materials within. Each color tells a story, a clue about the forces shaping the stars and the environment around them. Through this intricate study, scientists continue to unlock secrets about how stars are born, how they interact with their environments, and how they, in turn, influence the broader cosmic landscape. While the birth of stars is a breathtaking spectacle, the death of stars is equally dramatic and crucial to the continuing evolution of the universe. One of the most dramatic transformations in stellar evolution occurs when a white dwarf reaches the end of its life cycle. A white dwarf is a dense remnant of a star that has exhausted its nuclear fuel. After shedding its outer layers, the star's core remains, but without the heat and pressure needed to sustain nuclear fusion, the core begins to cool. Over time, this cooling process brings the white dwarf closer to the end of its existence. But in many cases, this quiet ending is not the final chapter for a white dwarf. In binary star systems, where two stars orbit closely together, the evolution of a white dwarf can take an unexpected turn. One of the stars in such a system may transfer mass onto its companion white dwarf, a process known as accretion. The white dwarf begins to accumulate material from its partner star, and as this matter builds up, the pressure and temperature at the core of the white dwarf increase. When these conditions become extreme enough, nuclear fusion is reignited in a cataclysmic explosion. This explosion, known as a Type 1 supernova, is one of the most energetic events in the universe. Within a matter of hours, a white dwarf can be transformed into a massive explosion that sends shockwaves through space. The core of the star is destroyed, and the outer layers are ejected in a burst of light and energy that can outshine an entire galaxy. The impact of a Type 1a supernova is not limited to its dazzling display of light. These explosions play a crucial role in the ongoing evolution of the universe. The elements created in the core of a star, such as carbon, oxygen, and iron, are scattered into the surrounding space during a supernova, enriching the interstellar medium with heavier elements. This process is vital for the formation of new stars and planets. Without these supernovae, the universe would lack many of the building blocks needed for life. The elements essential to life on Earth, including the carbon that forms the backbone of organic molecules, are forged in the hearts of stars and spread throughout the cosmos in these explosive events. Supernovae are, in essence, the universe's recycling mechanism, taking the products of stellar fusion and redistributing them to create the next generation of stars, planets, and possibly even life. The life cycle of stars, from birth to death, is a continuous process of creation and destruction. After a massive star exhausts its nuclear fuel, it can no longer support its own weight and collapses. The collapse leads to an explosion that releases a tremendous amount of energy, scattering the elements forged in the star's core into the surrounding space. These newly formed elements, ranging from the lightest hydrogen and helium to the heavier elements like carbon, oxygen, and iron, are ejected into the interstellar medium. Over time, these elements will mix with gas and dust, eventually giving rise to new stars and planetary systems. The explosion of a massive star thus marks the beginning of a new chapter in the cosmic story. The materials it releases contribute to the formation of new stars, planets, and other celestial bodies. The very elements that make up our planet and ourselves were once forged in the heart of stars, and through supernovae, they were scattered across the universe. The universe, it seems, is a never-ending cycle of creation and transformation, where each explosion, each star's death, paves the way for the birth of something new. And as stars continue to be born, live, and die, the dynamic, ever-changing fabric of the universe grows ever more complex and intricate, each generation of stars leaving behind its own unique mark on the cosmos. The process of stellar evolution is one of the most profound and dynamic aspects of the universe. Each generation of stars contributes to the ongoing transformation of the cosmos, not just through their mere existence, but through their life cycles, which ultimately forge the elements that make up the universe around us. These stars, from their birth to their explosive death, shape the very fabric of the cosmos, creating a constantly shifting, evolving landscape. Stars are not just points of light in the night sky. They are the engines that drive the chemical evolution of the universe. Through the process of nuclear fusion, stars synthesize heavier elements from lighter ones during their lifespans. This means that from the beginning of time, stars have been creating the building blocks for everything we know, the elements that make up planets, life, and even the stars themselves. However, the true significance of this process becomes clear only when we understand that stars eventually reach a point where their own life force fades, and they end their journey in dramatic, violent explosions. These explosions are not random events, but are intricately tied to the very structure of the universe. As stars explode, they release these elements, often heavy metals like iron, gold, and even uranium, into the vast expanse of space. The remnants of these explosions provide the raw materials for the next generation of stars, ensuring that the universe is constantly renewing itself. This cyclical process of star birth, life, death, and rebirth is what gives the cosmos its ever-changing nature. The energy released from these stellar explosions, called supernova, not only provides the necessary elements for new stars and planets, but also drives the ongoing evolution of the universe itself. This grand cosmic cycle illustrates the interconnectedness of all matter across time and space, showing that everything in the universe, from the tiniest speck of dust to the largest galaxies, is intimately connected. One of the most fascinating aspects of stellar evolution is the role of white dwarfs in this process. These stellar remnants, the dense cores of stars that have exhausted their nuclear fuel, often live out their final days in relative quiet before potentially undergoing a dramatic and catastrophic transformation. However, not all white dwarfs will undergo this explosive change. Only those in certain circumstances, typically those in binary systems where they can accumulate material from a companion star, are at risk of becoming a supernova. Before a white dwarf reaches the tipping point where it will explode, there are several key indicators that astronomers monitor. First, it's crucial to understand that not all white dwarfs are destined for this fate. In fact, most will remain stable for billions of years, slowly cooling and fading into the depths of space. The stars that are most likely to explode are those that interact with a companion star, drawing material from its atmosphere. As this material accumulates on the surface of the white dwarf, it begins to increase in mass. The white dwarf may accumulate hydrogen or helium, which, when reaching a critical point, can trigger a thermonuclear reaction that results in an explosion. One of the first signs of instability in a white dwarf is the buildup of material on its surface. This material, usually in the form of hydrogen or helium, comes from the companion star. As the white dwarf draws this material in, it begins to increase in brightness, and the atmosphere of the star may expand. This change signals the potential for instability, and if the buildup continues, it can eventually ignite a thermonuclear reaction. This process is not unlike the ignition of a fuse leading to a massive explosion, a chain reaction that begins with the accumulation of mass and culminates in a supernova. In addition to changes in brightness, another indicator of potential instability in a white dwarf is its increased luminosity. A sudden surge in the brightness of the white dwarf can indicate that pressure and temperature in the star's core are rising rapidly. This, in turn, suggests that the star may be nearing a critical point where explosive fusion will occur, triggering the release of an enormous amount of energy. The spectral analysis of a star is another crucial tool for astronomers in predicting a potential supernova. When a white dwarf accumulates material from a companion star, the composition of its outer layers changes. By analyzing the light emitted from the star, astronomers can detect changes in the spectrum, particularly the appearance of elements like carbon, which indicates that fusion processes are beginning to take place. The presence of these elements, along with fluctuations in the spectral lines, reveals vital information about the temperature and chemical composition of the white dwarf, helping scientists determine whether the star is approaching the point of explosion. Finally, astronomers also monitor the light curve of the white dwarf. The light curve is a graphical representation of the star's brightness over time, and fluctuations in this curve can be an early warning sign of instability. Sudden peaks or dips in brightness are typically the result of violent surface events, such as the eruption of material or rapid changes in the star's atmosphere. These fluctuations in brightness are often the harbingers of a catastrophic failure that will ultimately lead to the star's explosion. Through careful observation of these indicators, brightness, surface composition, spectral features, and changes in the light curve, astronomers are able to infer whether a white dwarf is about to undergo a dramatic and explosive transformation. This transition marks the end of the white dwarf's quiet existence and signals the beginning of a new chapter in the cosmic drama. Beyond the fate of individual stars, the cosmos is also home to other remnants from the early solar system, asteroids and comets. These objects, though originating from the same time period, have distinct differences in both composition and behavior, and these differences greatly influence their potential impact risk on Earth. Understanding the contrasting characteristics of asteroids and comets is crucial for assessing the dangers they pose to our planet. Asteroids are rocky and metallic objects that typically reside in the asteroid belt, located between the planets Mars and Jupiter. Their composition makes them relatively stable compared to comets. Since they are made of dense materials like rock and metal, asteroids are not as volatile as their icy counterparts. However, their relative stability does not mean they are without risk. When an asteroid enters Earth's atmosphere and impacts the surface, it can cause significant damage, particularly if it is large. The risk of such an impact is heightened by the fact that many asteroids have orbits that cross Earth's path, meaning that collisions are a real possibility. Comets, on the other hand, are composed largely of ice, dust, and gases. They originate from the outer solar system, particularly from regions like the Kuiper Belt and the Oort cloud, and travel on highly elliptical orbits that bring them close to the Sun. As a comet approaches the Sun, the heat causes its icy nucleus to sublimate, releasing gas and dust that forms the comet's characteristic glowing coma and tail. This process makes comets not only visually spectacular but also volatile, as they can fragment unpredictably. While comets can pose a serious threat, their long orbital periods generally make them less frequent visitors to the inner solar system compared to asteroids. In terms of impact risk, asteroids are a more immediate concern. This is because many asteroids have well-established orbits that bring them relatively close to Earth on a predictable schedule. Comets, while potentially catastrophic in the event of a collision, are less frequent in their visits to the inner solar system. However, both asteroids and comets share the potential for catastrophic impact, and their distinct characteristics help shape the nature and frequency of that risk. Understanding these differences is essential for scientists as they monitor near-Earth objects and develop strategies to protect our planet from possible collisions. Throughout Earth's long history, the geological record has preserved evidence of catastrophic events driven by asteroid impacts. One of the most significant of these events occurred roughly 66 million years ago, when a massive asteroid, estimated to be around 10 kilometers in diameter, struck the Yucatan Peninsula in what is now Mexico. The impact created the Chicxulub crater and unleashed an unimaginable amount of energy, equivalent to billions of atomic bombs. This catastrophic collision had a profound impact on the planet's climate, sending dust and debris into the atmosphere, obscuring sunlight and causing a dramatic drop in temperatures. This impact winter likely played a major role in the extinction of approximately 75% of all species on Earth, including both marine organisms and terrestrial dinosaurs. Geological layers from this period show a distinct boundary, known as the Cretaceous-Tertiary (KT) boundary, which is marked by a layer rich in iridium, an element commonly found in asteroids but rare on Earth. The presence of this layer provides irrefutable evidence of an asteroid impact and its global consequences. In addition to the Chicxulub impact, there are other examples of prehistoric collisions that have left their mark on the Earth's surface. One of the most notable is the large impact crater in the Sudbury region of Canada, which dates back about 1 billion years. Similar craters around the world tell the story of how asteroids have shaped the planet's history, leaving behind scars that reveal the dramatic effects of extraterrestrial collisions on Earth's environment. These craters, varying in size and age, provide a tangible record of the violent history of our planet illustrating the role that celestial bodies like asteroids and comets have played in shaping the Earth's geological history. As scientists continue to study these ancient impact sites, they gain valuable insight into the nature of these collisions and their long-lasting effects on the planet. By understanding the history of asteroid impacts and monitoring near-Earth objects today, we can better prepare for future collisions and safeguard our planet from the unpredictable forces of the cosmos. Throughout Earth's history, scientists have uncovered fascinating evidence that small but frequent impacts from asteroids have been far more common than previously thought. These impacts, often occurring over millions of years, are woven into the very fabric of our planet's geological story. The lunar surface with its multitude of craters serves as a preserved record of these cosmic collisions, primarily because the moon lacks the atmosphere and erosional forces that continuously reshape Earth's surface. While many of the impacts that Earth has experienced may have been too small to trigger mass extinctions, they still caused significant local disturbances, altering ecosystems in ways we are only beginning to understand. The geological evidence left behind by these impacts is both varied and vivid. From the immense, often sprawling craters scattered across the globe to the curious layers of iridium-rich deposits found in the Earth's crust, these signs paint a picture of a planet repeatedly shaken by celestial events. Some of the most significant events in Earth's history were likely catalyzed by asteroid impacts, triggering not only dramatic changes in the environment, but also reshaping the course of life itself. The deep scars left by these collisions are reminders of the chaotic forces at play in the universe. Each impact, whether a world-shaking event or a smaller, more localized one, altered the Earth in irreversible ways, leaving their imprint in the geological record. This ongoing research into Earth's impact history has fueled humanity's growing awareness of the risks posed by asteroids. We are no longer passive witnesses to these cosmic events. The reality of potential asteroid collisions is something that we are actively monitoring and, in some cases, mitigating with the hope of preventing catastrophic consequences. With a combination of scientific ingenuity, technological advances, and international collaboration, we are taking proactive steps to safeguard our planet from these celestial threats. The monitoring of near-Earth objects, NEOs, has become a critical area of focus. Astronomers and planetary scientists are leveraging cutting-edge technology to scan the skies for asteroids whose orbits bring them dangerously close to Earth. Through a network of ground-based observatories and space missions, we are continuously cataloging these objects, using a blend of observational techniques to track their movement and predict their paths. The aim is not only to detect these space rocks, but to gather critical data on their size, shape, composition, and most importantly, the trajectory that might bring them into Earth's path. A central feature of the global effort to monitor these potential threats is the collaboration among space agencies, scientists, and governments. Major players like NASA, the European Space Agency, ESA, and other international organizations are leading the charge in efforts to protect Earth from asteroid impacts. For example, NASA's Near-Earth Object Observations Program is dedicated to identifying and monitoring objects that could pose a threat to our planet. This program collects data not just on the asteroids themselves, but also assesses the likelihood of their collision with Earth, helping to create a comprehensive risk assessment for each object. In parallel with these detection efforts, numerous strategies for planetary defense are under investigation. One of the most talked about methods for diverting an asteroid from its course is the kinetic impactor technique. The concept is simple, yet groundbreaking: launching a spacecraft at an asteroid with enough force to change its trajectory. The key challenge lies in the precision required to ensure that the collision will alter the asteroid's path just enough to avoid a collision with Earth. This requires a precise understanding of the asteroid's mass, velocity, and composition, all of which must be accounted for in the planning of such an intervention. Another promising approach involves the use of a gravitational tractor. In this scenario, a spacecraft would position itself near an asteroid using its own gravitational pull to gently alter the asteroid's orbit over time. Unlike the kinetic impactor method, this technique would be far less dramatic, offering a more gradual and controlled way to steer an asteroid away from Earth. While this method may take longer to be effective, it presents a potentially safer and more predictable means of planetary defense. Collaboration among nations and scientific communities also plays a vital role in planetary defense. With data being shared across borders and a collective approach to identifying and mitigating asteroid risks, the international community is building a more robust defense infrastructure. Astronomers and planetary scientists regularly meet to update each other on the latest findings, ensuring that the information we have about asteroids is as current and accurate as possible. Furthermore, early warning systems are being developed to alert the public and governments about potential asteroid threats, enabling humanity to prepare for any eventualities. Through these combined efforts, the scientific community is actively working to ensure that we are not only aware of the risks posed by asteroid collisions, but also prepared with effective strategies to defend our planet. The investment in both detection and deflection technologies will significantly improve our chances of avoiding future disasters, ensuring that we can continue to thrive without the constant fear of catastrophic asteroid impacts. Beyond the immediate threat posed by asteroids, there are other phenomena in the cosmos that continue to captivate the imaginations of scientists and the public alike. One such phenomenon is planetary ingress, which refers to the movement of one celestial body, like a planet, into a particular position relative to another astronomical object, such as a star or a neighboring planet. This realignment of celestial bodies can lead to observable changes in the way the universe appears to us from Earth. Imagine the planets as dancers in an elegant celestial ballet, their orbits shifting and realigning in ways that can create dramatic effects on the light we see from our vantage point. When one planet passes in front of a star, for example, it can temporarily block some or all of the light from that star, resulting in a dimming effect. This is not only a beautiful celestial event, but also a useful phenomenon for astronomers. Astronomers have long used planetary ingress, specifically the transit method, to study distant exoplanets. When a planet passes in front of its parent star, the amount of light it blocks can tell scientists a great deal about the planet itself. By measuring the dimming of the star, astronomers can infer details about the planet's size, its orbital characteristics, and even gain insight into its atmosphere by analyzing how the light filters through it. This technique has been crucial in identifying and studying exoplanets beyond our solar system. Planetary ingress can also have broader implications for the gravitational interactions between celestial bodies. When planets align during these events, their combined gravitational pull can create subtle disturbances or perturbations in the orbits of neighboring objects. Over long periods, these slight changes can accumulate, leading to shifts in the orbits of smaller celestial bodies. These gradual shifts can eventually result in more dramatic outcomes, such as altering the path of a planet or even triggering the collision of two celestial objects. On a more massive scale, significant planetary ingress events can lead to chaos within a solar system. If a large planet moves into the vicinity of smaller celestial bodies, its gravity could disrupt their orbits, sending asteroids careening off course or even ejecting moons from their orbits. Such cosmic upheavals remind us of the fragility of celestial systems and the interconnectedness of the universe. A single change in the position of one body can have cascading effects across vast distances, reshaping the entire dynamic of a solar system. Now, imagine a scenario in which a planetary ingress occurs with a large planet entering the space occupied by Earth and its moon. The implications of such an event would be profound, with potentially far-reaching consequences for both Earth and its closest natural satellite. The gravitational influence of the new planet would exert a strong force on the Earth-Moon system, which could lead to significant alterations in the Moon's orbit. Depending on the mass and proximity of the incoming planet, the changes in the Moon's path could range from subtle to catastrophic. If the new planet's gravitational force were strong enough, it could pull the Moon closer to Earth, leading to stronger tidal forces. The resulting rise in tides could cause catastrophic flooding in coastal regions, threatening ecosystems and human settlements alike. On the other hand, if the moon were pushed outward, its orbit could be destabilized, leading to diminished tidal forces. This could disrupt the delicate balance that has existed for millions of years, throwing off the natural rhythms that govern life in the oceans and along coastlines. In an even more dramatic scenario, if the gravitational forces were overwhelmingly strong, the new planet could capture the moon, pulling it into orbit around itself. This would mark the end of the moon's relationship with Earth, as it would no longer orbit our planet. Such an event would fundamentally alter the dynamics of both the Earth and the moon. Over time, the effects could include changes in Earth's rotation, lengthening or shortening the day, and even potentially altering the planet's climate patterns. The possibility of planetary ingress is a reminder of the vast and unpredictable nature of the cosmos. Even the slightest shift in the position or movement of celestial bodies can lead to monumental changes, affecting not just the objects directly involved, but also the entire solar system. The interconnectedness of the universe ensures that no event, however distant, is truly isolated. It's a sobering thought, but it's also a testament to the incredible complexity of the universe we inhabit. A sudden shift in the moon's position could set off a chain reaction of geological stresses, both on the moon and on Earth. This disturbance might be more than just an unsettling cosmic anomaly. It could unleash seismic activities on both bodies. The gravitational tug between Earth and the moon is a delicate balance, one that governs much of the dynamics of our planet's tides, rotation, and even the geological stability of our Earth. If the moon's position were to change abruptly, this tug could trigger seismic shifts, changing the landscape on the moon's surface in unpredictable ways and potentially leading to earthquakes on Earth. The effects wouldn't just be localized. They could send shockwaves through the entire Earth-Moon system, altering tides, disrupting ecosystems, and reshaping the delicate gravitational relationship that has existed for eons. The moon, long a steadfast companion in the night sky, would no longer just be a silent observer, but an active participant in a complex and unpredictable cosmic dance. This dance could have far-reaching consequences, affecting everything from the rhythms of life on Earth to the very way our celestial neighborhood interacts. Gravitational forces are not merely a background influence on celestial mechanics. They are the primary actors in a variety of planetary ingress scenarios. Planetary ingress refers to the process by which a celestial object, be it a meteorite, asteroid, or spacecraft, enters a planet's atmosphere. As an object approaches a planet, it experiences the powerful gravitational pull of that planet, drawing it closer. The closer the object gets, the stronger this force becomes, accelerating the object as it nears the planet's surface. This acceleration isn't just an abstract concept. It transforms the object's potential energy into kinetic energy, which results in an increase in speed. The faster the object travels, the greater the impact it will have upon entering the atmosphere. The object's velocity as it crosses the boundary between space and atmosphere is of paramount importance. As the object enters the denser layers of the atmosphere, it encounters a resistance that increases with its speed. This resistance is not a passive force. It actively generates heat, sometimes to extreme levels, depending on the object's size, speed, and the density of the atmosphere it's entering. This is where gravitational forces play an even more critical role. Not only do they influence the object's speed and trajectory, but they also determine how much atmospheric friction the object will encounter. A high-speed object will face a greater buildup of heat, which could lead to the disintegration of smaller objects like meteoroids before they even reach the planet's surface. For larger objects, this gravitational influence can lead to a dramatic impact. Whether it burns up upon entry or reaches the surface intact, gravitational forces will ultimately dictate the object's fate. In the case of human-made spacecraft, gravity continues to play a determining role, but in this case, the forces are harnessed. Controlled descent mechanisms, such as parachutes or retrorockets, work in concert with the gravitational field to slow the spacecraft's descent and ensure a safe landing. Understanding the intricate relationship between gravity, speed, and atmospheric resistance is crucial not only for understanding natural events like meteorite impacts, but also for ensuring the success of space missions. This knowledge is essential for humanity as we explore further beyond our planet into the vast unknown of our solar system and beyond. Solar flares are another example of the powerful forces that govern our relationship with the cosmos. These bursts of energy and radiation emanating from the sun's surface represent a dynamic and unpredictable phenomenon in the solar system. Solar flares occur when the sun's magnetic fields become twisted and tangled, particularly in the regions known as sunspots. Imagine the sun's magnetic field as a vast elastic sheet, stretched and stressed by the constant flow of solar activity. When these magnetic fields snap back into a more stable configuration, they release an immense amount of energy. This energy propels a mass of charged particles into space at incredibly high speeds, causing what we recognize as solar flares. These flares aren't just beautiful displays in the sky, they have the potential to disrupt life on Earth in a variety of ways. When solar flares release their radiation, the electromagnetic energy spreads out across the solar system, reaching Earth. This energy spans a wide spectrum of wavelengths, including visible light, ultraviolet radiation, and even X-rays. When this radiation reaches Earth, it interacts with the ionosphere, the part of the atmosphere that helps facilitate radio communications. The ionosphere is a delicate and finely tuned layer of charged particles, and when the energy from a solar flare reaches it, the result can be disruptive. Radio signals, both on the ground and those traveling through space, can experience interference, leading to blackouts. This can affect communications between ground stations and satellites, as well as disrupt the navigation systems that rely on satellite signals. For example, GPS signals could become unreliable, making it difficult for travelers or pilots to find their way. But the effects of solar flares don't stop at communications. They extend into the very infrastructure that supports modern society. In extreme cases, solar flares can produce geomagnetic storms, which are disturbances in Earth's magnetic field caused by the influx of charged particles from the sun. These storms can induce electrical currents in power grids, potentially leading to widespread power outages. The intensity of these storms can be severe enough to damage satellites in orbit, knock out communication links, and even cause a temporary shutdown of power systems. While these solar events are natural phenomena, their impact on human technology is profound. They remind us of the complex interconnection we share with the sun. What might seem like a distant, unpredictable event can ripple through our technological systems and disrupt life on Earth. Fortunately, recent advancements in space weather prediction have improved our understanding of solar flares and their effects. Scientists have developed more sophisticated tools for observing the sun's activity and predicting when these explosive events are likely to occur. Among the most notable developments in solar observation are the advanced spacecraft that continuously monitor the sun's surface and atmosphere. One such spacecraft, the Solar Dynamics Observatory, provides real-time images and data of solar flares, sunspots, and other forms of solar activity. By observing the sun's behavior in such detail, researchers can identify patterns in its activity that are linked to solar flares. This data enables scientists to predict flare events with increasing accuracy. In addition to observational tools, machine learning algorithms have been applied to solar flare research. These algorithms allow researchers to process vast amounts of data more rapidly than ever before, identifying patterns and correlations that might otherwise go unnoticed. By training these systems on historical flare data, scientists can create predictive models that offer lead times for solar flare events, giving Earth-based systems more time to prepare. This predictive power is invaluable when it comes to protecting satellites, communication systems, and power grids from the potentially devastating effects of solar activity. In the end, solar flares, like other cosmic events, highlight the intricate and unpredictable forces at play in our solar system. The sun's magnetic fields shape the path of solar radiation, and gravity influences everything from the trajectory of meteorites to the survival of spacecraft. Whether it's the effect of a gravitational shift on the moon or the disruption caused by a solar flare, these celestial forces remind us of our place in the grand cosmic web, always interconnected and influenced by the immense, unpredictable forces of the universe. In recent years, global collaboration among countries and space agencies has led to a much more refined and holistic approach to monitoring solar activity. This cooperative effort has brought together data from a wide array of satellites, providing researchers with an unparalleled understanding of solar behavior. As this network of observation grows and becomes more sophisticated, scientists have enhanced their ability to predict and respond to solar flares, those sudden bursts of radiation from the sun that can send powerful waves of charged particles towards Earth. The stakes of this research are high, as solar flares not only have the potential to disrupt technological systems, but can also pose risks to human safety. Solar flares are by their very nature energetic events, capable of significantly affecting the Earth's atmosphere and its magnetic field. Their disruptive influence can reach across vast distances in space, making the need for accurate forecasting and swift response even more crucial. In the past, when solar flares erupted, the world was often caught off guard, struggling to mitigate the impacts on infrastructure that was not designed to handle such extreme phenomena. However, as our technological tools continue to advance, so too does our ability to track, predict, and, importantly, protect society from these potent solar events. Historically, humanity has witnessed firsthand the formidable power of solar activity. One of the most famous solar storms in recorded history was the Carrington event of 1859. This solar flare unleashed an intense wave of charged particles that collided with Earth's magnetic field, creating an incredible spectacle of auroras. These glowing lights could be seen as far south as the Caribbean, where they were a rare and mesmerizing sight. Yet the beauty of the auroras was accompanied by a more ominous consequence. Telegraph systems across North America and Europe were disrupted. Telegraph operators reported receiving electrical shocks, and in some cases, the electrical surges were so intense that entire telegraph stations caught fire. The Carrington event stands as a stark reminder of the potential for solar flares to cause significant disruptions, especially when our technology is not prepared for such surges in electrical energy. Fast forward to the late 20th century, when the world's dependence on electrical power and communication systems had reached unprecedented levels. In 1989, a solar flare triggered a geomagnetic storm that caused widespread power outages across Quebec, Canada. Millions of people were left without electricity for several hours, a vivid demonstration of the vulnerability of modern infrastructure to solar activity. In addition to the loss of power, the storm also wreaked havoc on communication systems and transportation networks, showing just how much we had come to rely on systems that are inherently susceptible to space weather. This event highlighted the urgent need for more robust protective measures, as solar flares have the potential not just to disrupt communication networks, but also to damage critical infrastructure that is essential to modern life. In the years that followed, solar storms continued to pose challenges. One such event occurred in 2003 when a solar flare triggered a series of malfunctions in communication satellites and interfered with radio transmissions. Though the damage from this event was less severe than the Carrington event or the 1989 storm, it nevertheless served as a powerful reminder of how much more dependent society has become on technology that can be easily affected by space weather. While humanity's reliance on technology grows, so does the need to better understand and prepare for the potentially disruptive power of solar activity. These historical incidents underscore the intricate relationship between the sun's activity and life on Earth, a relationship that is not only a source of beauty, but also one of caution. They highlight both the allure and danger inherent in the forces of nature that lie just beyond our atmosphere. As our understanding of the sun and its behavior deepens, scientists are constantly improving their ability to predict solar events and to safeguard technology from their effects. Innovations in solar monitoring and space weather forecasting are becoming increasingly effective at anticipating solar flares and their potential impacts. With these advancements, we now have a clearer picture of how solar activity interacts with Earth's magnetic field and atmosphere, allowing us to develop better strategies for mitigating the potential risks. These improvements in solar monitoring are crucial for not just protecting our infrastructure, but also ensuring the safety of our technology-dependent society in the face of future solar events. At the same time, space scientists have also turned their attention to interstellar clouds, vast regions of gas and dust that occupy the space between stars. These clouds, often referred to as the raw material of the universe, are primarily composed of hydrogen, with small amounts of helium and other elements mixed in. While they may seem like mere voids in space, these clouds are anything but passive. They play a crucial role in the formation of stars and planetary systems, influencing the cosmic landscape in profound ways. Interstellar clouds are more than just collections of gas and dust. They are the birthplace of new stars. When certain regions within these clouds become dense enough due to gravitational attraction, the material begins to collapse under its own weight. This process initiates the birth of a new star as the central core heats up and ignites nuclear fusion. In this way, interstellar clouds are responsible for regulating the cycle of stellar life, dictating when and where new stars will form. This role is crucial to the evolution of galaxies, as it ensures a continual process of star formation, enriching the universe with the light and energy that drives much of cosmic activity. In addition to their role in star formation, interstellar clouds also serve as a laboratory for chemical reactions. The dense environments within these clouds facilitate the creation of complex molecules, including organic compounds that could potentially serve as the building blocks of life. As these clouds evolve, they release these elements into their surroundings, enriching nearby regions with the raw materials necessary for planetary formation. In this sense, interstellar clouds not only contribute to the birth of stars, but also to the creation of the very elements that make life possible. But the influence of interstellar clouds doesn't stop there. Some of these clouds are buoyant, floating through space and interacting with nearby stars and cosmic environments. These clouds can influence the radiation emitted by stars, altering their stellar winds and the types of radiation they produce. Furthermore, when massive stars explode in supernovae, they can compress the gas and dust in nearby clouds, triggering new waves of star formation in a chain reaction. This dynamic interaction between stars and interstellar clouds is just one example of the interconnectedness of the cosmos, where the death of one star can give rise to the birth of others. It's also worth noting that an encounter with a dense interstellar cloud could have significant consequences for our solar system. If the sun's journey through the galaxy were to bring it into closer proximity to such a cloud, the increased density of material could disrupt the solar wind, the stream of charged particles that the sun continuously emits. The solar wind plays a critical role in shaping the space environment around Earth and the other planets, and any disruption to its flow could have profound effects on the solar system's magnetic fields. If the solar wind were to be impeded, it could result in increased levels of cosmic radiation reaching the Earth, which would not only have implications for life, but also for our technological systems. In addition to altering the solar wind, an encounter with an interstellar cloud could potentially initiate new cycles of star formation. As material from the cloud interacts with the existing gas and dust of the solar system, it could create regions of higher density that spark the birth of new stars. This could lead to the formation of new stellar bodies within our solar vicinity, or even trigger the creation of new planetary systems in nearby regions of space. Moreover, the material from the cloud could interact with existing celestial bodies, altering their chemical composition and potentially influencing their potential for supporting life. The experience of encountering an interstellar cloud would be a powerful reminder of the complex and delicate balance that governs the universe. These clouds, with their influence on star formation, chemical evolution, and the behavior of cosmic radiation, are not mere backdrops to the larger drama of the cosmos. They are active, dynamic entities that shape the future of stars, planets, and even life itself. In conclusion, the relationship between the sun's activity, space weather, and interstellar clouds is an intricate web of interconnected forces that influence not just the immediate space around us, but the very building blocks of the universe itself. Understanding these phenomena, how they interact with our planet, how they shape the development of stars and planets, and how they can influence life on Earth, is essential to comprehending the universe's vast, ever-evolving story. As our scientific capabilities continue to evolve, so too will our ability to unravel the mysteries of these cosmic forces, providing us with deeper insights into the nature of space, time, and the forces that govern all existence. Throughout the vast expanse of space, the study of cosmic clouds has become one of the most compelling areas of research for scientists, offering profound insights into the life cycle of stars and the larger structure of galaxies. Cosmic clouds, essentially vast accumulations of gas and dust, serve as the birthplace of stars and the remnants of celestial phenomena that have shaped the universe over billions of years. These clouds come in many forms, each playing a pivotal role in stellar formation and evolution. The exploration of their intricate dynamics has opened new frontiers in our understanding of the cosmos, shedding light on the processes that give rise to stars, planets, and even the conditions that might support life as we know it. Researchers are currently delving deep into how different types of cosmic clouds contribute to the various stages of star formation. One type of cloud that has garnered significant attention is the dark nebula, a dense mass of gas and dust that obscures the light of stars and other celestial objects lying behind it. These dark nebulae act as stellar nurseries, regions where new stars are born from the collapsing gas. Because they block visible light, they are often invisible to traditional telescopes, but with the advent of infrared technology, scientists can peer through the dust to observe the early stages of star formation. In stark contrast, there are also bright emission nebula, which glow with vibrant colors due to the intense radiation emitted by nearby hot stars. These nebulae are a testament to the dynamic interplay between gas and light. The high-energy radiation from these young stars ionizes the surrounding gas, causing it to emit light. These emission nebulae are crucial for understanding the end stages of stellar formation, as the energy released by the stars can influence the cloud's temperature, density, and overall structure. Each type of nebula, whether dark or bright, provides a unique glimpse into the different phases of the stellar life cycle. From the birth of new stars in the dense, cold regions of dark nebulae to the explosive energy shaping the fate of gas in bright nebulae, these clouds are central to our understanding of how stars come into being, evolve, and eventually die. But the role of cosmic clouds extends beyond the creation of stars. In the grander scheme of galactic evolution, these clouds are often the remnants of supernovae, the explosive deaths of massive stars. When a star reaches the end of its life and explodes in a supernova, it disperses heavy elements into the surrounding space, enriching the interstellar medium. This process is crucial because the elements produced in these stellar explosions, such as carbon, oxygen, and iron, are the building blocks for the formation of new stars, planets, and even the conditions necessary for life. In this ongoing cosmic cycle, the material left behind by dead stars is recycled into new clouds, providing the raw materials for future generations of stars. This constant recycling of matter not only contributes to the creation of stars and planetary systems, but also plays a vital role in the development of galaxies over the course of billions of years. Advanced telescopes and observational technologies have allowed scientists to gain new perspectives on these cosmic clouds, revealing their complex structures, movements, and interactions. Through detailed observations, researchers are gaining valuable insights into how these clouds with one another, how magnetic fields influence their behavior, and how radiation from nearby stars affects their composition and evolution. Understanding the dynamics within these clouds and between them is essential for uncovering the mysteries of the universe. The study of cosmic clouds is not just about understanding how stars and planets are born, but also about exploring the fundamental forces at play in the universe. It is this research that is slowly unraveling the complex history of galaxies and helping scientists piece together the evolution of our universe over the vast expanse of time. Equally captivating, pulsars, another extraordinary product of stellar evolution, have become a focal point for astronomers and physicists seeking to understand the nature of matter and the forces that govern the cosmos. Pulsars are neutron stars, the remnants of massive stars that have gone supernova. These stars are incredibly dense, composed primarily of neutrons, which are the neutral particles found in the nucleus of an atom. The collapse of a massive star's core under the force of gravity leads to the creation of a neutron star. The density of these objects is mind-boggling. Just a cubic centimeter of neutron star material would weigh as much as a mountain here on Earth. This immense density arises because the gravitational forces are so powerful that they compress the star's core to a point where protons and electrons merge to form neutrons. The extreme nature of neutron stars gives rise to pulsars, which are rapidly rotating neutron stars that emit beams of electromagnetic radiation. These beams can span a wide range of wavelengths, including radio waves, visible light, and X-rays. As the pulsar spins, these beams sweep across space, much like the light from a lighthouse. When the beams are directed toward Earth, we perceive them as pulses, which is why these objects are called pulsars. The rotation of pulsars can be incredibly fast. Some rotate hundreds of times per second, making them one of the most fascinating phenomena in the universe. The intense magnetic fields surrounding pulsars are another key feature. These fields can be trillions of times stronger than Earth's magnetic field, capable of accelerating charged particles to near light speed. These high-energy particles emit radiation, creating the brilliant beams that we observe. In binary systems, where a pulsar is paired with another star, material from the companion star can be drawn toward the pulsar, fueling intense bursts of energy, particularly in the X-ray spectrum. These interactions further highlight the pulsar's role as a cosmic beacon, illuminating the extreme conditions present in the universe. Pulsars are not just fascinating in their own right, they also provide scientists with valuable tools for exploring some of the most fundamental aspects of physics. One of the most remarkable features of pulsars is their ability to act as a cosmic clock. Their regular pulses can be used to measure time with incredible precision, offering a means of testing theories of gravity and understanding the behavior of matter under extreme conditions. Pulsars have proven invaluable in the study of relativistic physics, helping scientists test predictions made by Einstein's theory of general relativity. The precise timing of their pulses can be used to study phenomena such as gravitational waves, ripples in space-time caused by the acceleration of massive objects. Additionally, pulsars in binary systems provide an excellent laboratory for studying the effects of gravitational interactions between two stars. By analyzing the motion of the pulsar and its companion star, scientists can gain a deeper understanding of the nature of gravity, space-time, and the behavior of matter in extreme environments. Pulsars also serve as natural probes for studying the interstellar medium. As their beams pass through space, they interact with the particles and magnetic fields present between stars, providing scientists with a unique opportunity to assess the composition of the material that exists between stars. Even more intriguing are the glitches that pulsars occasionally experience. These glitches, which are sudden and unexpected changes in the pulsar's rotation rate, offer important clues about the inner workings of neutron stars. They suggest the presence of a superfluid state of matter deep within the pulsar's core, a state that cannot be replicated on Earth. Understanding these glitches helps scientists explore the extreme conditions within neutron stars and provides insights into the nature of matter at densities and temperatures far beyond what we can recreate in a laboratory. Despite the many ways in which pulsars are used to explore the universe, they are not without their dangers. If Earth were ever to come too close to a pulsar, the consequences could be catastrophic. The beams of radiation emitted by a pulsar are incredibly concentrated, and if Earth were to enter their path, the radiation levels could exceed those we experience from the Sun by many orders of magnitude. This intense radiation could strip away the Earth's atmosphere, expose the surface to harmful radiation, and severely disrupt ecosystems. The powerful magnetic fields of pulsars could also have disastrous effects on our planet. If Earth were to enter such a magnetic field, it could distort our own magnetic environment, disrupting everything from satellite communications to power grids, making modern technology virtually useless. In the most extreme cases, the radiation emitted by a pulsar could create an environment so hostile to life that it might lead to the extinction of most species on Earth. This highlights just how powerful and dangerous these celestial objects can be. Despite their relatively small size in comparison to other astronomical phenomena, pulsars wield an immense amount of energy and influence, underscoring the dramatic and unpredictable nature of the universe. Ultimately, pulsars serve as both natural laboratories and cautionary tales, offering a unique window into the workings of the universe while also demonstrating the potential hazards that lie beyond our planet. These celestial objects continue to captivate scientists, providing endless opportunities for discovery and expanding our understanding of the fundamental forces that govern the cosmos. Through the study of pulsars, cosmic clouds, and the countless other phenomena scattered throughout the universe, researchers are peeling back the layers of space and time, slowly but surely revealing the intricate tapestry of our universe's history. The universe, as vast and perplexing as it is, holds numerous phenomena that challenge the boundaries of our understanding. Among the most intriguing and enigmatic objects in the cosmos are pulsars, which are the remnants of massive stars that have exploded in supernovae. These cosmic beacons emit beams of radiation that can be detected from across the universe, offering us a glimpse into the extreme physics that govern their existence. Some pulsars, particularly millisecond pulsars, stand out for their remarkable characteristics. These objects spin at an extraordinary rate, completing a full rotation many times per second. This rapid rotation results in beams of energy emitted with an astonishing precision and stability, making them invaluable tools for astronomers and physicists alike. Millisecond pulsars in particular provide an exceptional opportunity to test the fundamental theories of physics, including those related to gravity and the theory of general relativity. Their predictability and extreme regularity make them excellent candidates for experiments aimed at pushing the boundaries of our knowledge. As these pulsars rotate at such incredible speeds, they present an almost ideal environment to probe the nature of space-time itself. With each discovery, the understanding of these remarkable objects deepens, and in turn, our grasp of the most extreme phenomena in the universe grows. What we are learning from pulsars is not just about these objects in isolation, but about the nature of the universe itself, as we explore the most powerful forces at play in the cosmos. One of the most fundamental and awe-inspiring theories that has revolutionized our understanding of the universe is the theory of cosmic inflation. This theory posits that in the earliest moments of the universe, right after the Big Bang, the cosmos experienced an incredibly rapid expansion. To put this into perspective, imagine a balloon that is initially smaller than the size of an atom. Within a fraction of a second, this tiny balloon began inflating at an exponential rate, growing many times its original size. This momentary but incredibly rapid expansion is known as cosmic inflation. While it may sound almost incomprehensible, this theory provides an elegant solution to several pressing puzzles in cosmology, such as why the universe appears to be so uniform in all directions, the vast distance between objects. During the inflationary phase, the universe expanded at a rate faster than the speed of light. While this notion might seem counterintuitive, it's crucial to understand that the stretching occurred not through the motion of objects through space, but through the fabric of space itself expanding. This distinction is vital to grasping the concept of inflation. As space-time itself stretched, it essentially smoothed out any initial irregularities in the universe. This process led to a homogeneous and isotropic cosmos, meaning that no matter where one looks, the universe appears to be essentially the same in all directions. This smoothness, established during inflation, set the stage for the formation of all that we see in the universe today. However, it wasn't just the uniformity of the universe that was set into motion by inflation. The tiny quantum fluctuations that existed in the very first moments of the universe became the seeds for the vast cosmic structures we observe. These fluctuations, although minuscule, had a profound effect on the growth of the universe. Over time, these tiny variations in energy and density became the regions of space where matter began to clump together, eventually forming galaxies, stars, and clusters of galaxies. This process, known as structure formation, was driven by the very fluctuations that occurred during inflation. Thus, the influence of cosmic inflation cannot be overstated. It played a central role in shaping the large-scale structure of the universe and continues to serve as a fundamental framework for understanding how the cosmos evolved from its initial, hot, dense state to the complex, vast, and intricate universe we see today. Without the theory of inflation, much of our current understanding of the cosmos would be incomplete. The theory provides a framework that not only explains the large-scale structure of the universe, but also addresses key questions about its origins and evolution. The process of inflation effectively solves some of the most perplexing problems in cosmology, such as the flatness problem, why the universe appears to be so flat on large scales, and the horizon problem, why distant regions of the universe appear so similar despite being causally disconnected. Moreover, inflation suggests that the universe underwent a dramatic and extremely rapid growth phase, which directly impacted the distribution of matter and energy throughout space. As researchers continue to explore cosmic inflation, new questions arise. For instance, what would happen if the inflationary period were to suddenly change? Could such a shift dramatically alter the structure and dynamics of the universe? Such possibilities are not just theoretical. They could have profound implications for galaxies, including our own Milky Way. Imagine the universe as a balloon once again, rapidly inflating. If the rate of inflation were to suddenly change, it could lead to a ripple effect that would alter the expansion rate of the universe. A sudden speed up in inflation could push galaxies apart at an even faster rate, potentially stretching them out or even creating new galaxies in the spaces between existing ones. Conversely, if inflation were to slow down abruptly, the result could be an increase in gravitational attraction, which could pull galaxies closer together. Such a change could trigger interactions or mergers between galaxies, potentially leading to the formation of new structures in the cosmos. These shifts could have dramatic consequences for the evolution of galaxies, including the Milky Way. Not only would the overall structure of the galaxy be affected, but the fates of individual stars and planetary systems could change as well. For example, changes in the surrounding cosmic landscape could alter the paths of asteroids and comets, leading to more frequent collisions and interactions. Such events could disrupt existing planetary systems or create new opportunities for the formation of habitable environments on distant planets. The very nature of the universe is shaped by these cosmic processes, and understanding how they work could unlock new insights into the future of our galaxy and others like it. The theory of cosmic inflation also raises intriguing questions about the larger structure of the cosmos. Some scientists have proposed that inflation could be a recurring process, occurring multiple times throughout the universe's history. In this view, different regions of space might undergo inflation at different times, potentially leading to the existence of multiple universes in a broader multiverse. This idea, often referred to as eternal inflation, suggests that our universe could be just one of many, each with its own distinct properties and evolution. The idea of a multiverse opens up a whole new realm of speculation and research, as it challenges our understanding of what constitutes the universe, and raises questions about how we might observe or test the existence of other universes. At the heart of these discussions lies the question of what triggered inflation in the first place. Some scientists propose that tiny quantum fluctuations, minuscule variations in energy on the smallest scales, could have been responsible for the rapid expansion of the universe. Others suggest that certain fields in the universe, perhaps still unknown, may have played a crucial role in initiating inflation. As research continues, these questions remain at the forefront of cosmology, with scientists working tirelessly to uncover the mechanisms that triggered the universe's expansion and the conditions that allowed it to happen. The debate surrounding cosmic inflation is far from settled, and new theories and observations continue to shape our understanding of this pivotal moment in the universe's history. Whether inflation is a one-time event or an ongoing process, its impact on the cosmos is undeniable. The expansion of the universe in the moments following the Big Bang set in motion a chain of events that led to the formation of the structures we see today, from galaxies to stars, and even the conditions necessary for life to exist on Earth. As our ability to observe and understand the universe continues to evolve, the study of cosmic inflation promises to reveal even more about the forces and phenomena that govern the cosmos, providing deeper insights into the mysteries of existence itself. As we continue to explore the farthest reaches of space, the understanding of these fundamental processes will guide future discoveries. The interplay between pulsars, cosmic inflation, and the dynamics of the universe opens up an exciting frontier for both theoretical and observational astrophysics. Each step forward in this journey not only brings us closer to understanding the universe's most profound mysteries, but also enhances our ability to explore and interpret the vast, complex tapestry that stretches out across the cosmos. From the spinning pulsars to the rapid inflation that shaped the early universe, the quest for knowledge continues to fuel the scientific pursuit, driving us further into the unknown. Linking inflation to cosmic observations remains one of the most challenging and intriguing tasks in modern cosmology. While numerous features observed in the universe today align well with inflationary models, certain anomalies have continued to provoke scientists, urging them to reconsider the full accuracy of the theory. As our observational capabilities have expanded, particularly with the advent of more advanced telescopes and satellites, the growing body of data has revealed both striking confirmations of the inflationary hypothesis as well as compelling inconsistencies that suggest our current understanding may require refinement or perhaps a more profound paradigm shift. For example, the cosmic microwave background, CMB, radiation, a crucial piece of evidence supporting the inflationary model, has shown unexpected patterns that challenge the straightforward assumptions about the early universe. These anomalies are not just minor statistical deviations, but may hint at deeper physical processes that our models have yet to fully account for. Similarly, the distribution of galaxies in the cosmos, once thought to be a straightforward outcome of inflationary expansion, has presented intriguing irregularities. These inconsistencies have led some cosmologists to hypothesize that we may be overlooking essential components or mechanisms in the inflationary model that could better explain the observed structures of the universe. Equally elusive is the nature of the fields that drive cosmic inflation. The leading candidates, scalar fields, propose an energy density that provides the necessary conditions for inflation to occur. However, even within this framework, there is significant debate over the precise characteristics and behaviors of these fields. Different models suggest varying mechanisms, from more simple forms of scalar fields to more complex structures that involve multiple fields interacting in intricate ways. This lack of consensus has kept the field in a constant state of evolution, as each new observational data set brings the scientific community one step closer to understanding which model most accurately describes the physics of the early universe. The search for the right inflationary model is far from over, and as new data streams in from increasingly sophisticated instruments, the dialogue continues to evolve, potentially offering new insights or even entirely new paradigms in cosmology. As these efforts unfold, the story of cosmic inflation evolves not as a single narrative, but as a dynamic process, constantly adapting to the ever-expanding frontier of observational science. The more we discover, the clearer it becomes that our understanding of the universe's inception is far from complete, and the ongoing research into inflation holds the potential for monumental breakthroughs that could rewrite the textbooks on cosmology. The journey, one that constantly challenges and reshapes our assumptions, underscores the importance of continuing to explore, question, and refine the theories that shape our understanding of the cosmos. Turning from the large-scale universe to the dynamic processes within stars, we encounter a fascinating phenomenon known as star quakes, or stellar flares. These seismic events, originating deep within the interiors of stars, are driven by the intense pressures and temperatures that characterize stellar environments. To visualize this, imagine the heart of a star as an immense boiling pot, where nuclear fusion, the very process that powers stars, takes place under conditions of unimaginable heat and pressure. As the energy levels within a star fluctuate, sudden releases of built-up energy can cause violent disruptions. These disruptions, or oscillations, generate waves that ripple through the star's material in much the same way that stones create ripples across a pond's surface. Detecting star quakes from Earth is no small feat. It requires the use of highly sophisticated technology, including state-of-the-art telescopes equipped with sensitive instruments capable of detecting the faintest vibrations and the subtlest shifts in light emanating from distant stars. These instruments analyze the light spectrum, which holds the unique signatures of the various elements within a star. By scrutinizing these fluctuations in brightness and color, scientists can infer the occurrence of a star quake. More advanced telescopes can even capture the minute vibrations that reverberate through a star's surface, offering a window into the processes taking place beneath the stellar exterior. Through the study of these oscillations, astronomers can gain invaluable insights into the internal structure of stars and the complex forces that govern their behavior. Just as seismologists study the tremors caused by earthquakes on Earth to understand our planet's internal makeup, astronomers use the signals from starquakes to probe the inner workings of stars. This research not only deepens our knowledge of stellar activity, but also enhances our understanding of stellar life cycles, how stars are born, evolve, and eventually die. While starquakes may seem similar to the seismic activities we experience on Earth, they arise from entirely different processes. On Earth, seismic activity is primarily the result of tectonic plate movements, shifts in the planet's crust caused by the heat generated deep within the Earth. These movements lead to the familiar shaking tremors and earthquakes that reshape the planet's surface. On the other hand, star quakes occur within the very structure of the star itself, driven by dynamic forces such as convective flows and oscillations that take place under the extreme pressures and temperatures found within stars. Instead of tectonic plate movements, star quakes are caused by disruptions in a star's fusion process or magnetic field interactions. The scale of star quakes dwarfs that of earthly earthquakes. The amount of energy released during these stellar events is staggering, with waves that travel through the star itself, potentially altering its overall structure. Observing these waves provides a unique opportunity to learn more about the star's internal processes, just as studying seismic waves from earthquakes helps us understand the geological processes within our planet. While starquakes and earthquakes share a name, they represent vastly different cosmic phenomena, reflecting the unique and sometimes bewildering dynamics of the universe. Starquakes, while fascinating in their own right, hold profound implications, especially when they occur in nearby stars. The energy released during such an event can have far-reaching consequences. If a starquake were to happen in a star within our local galactic neighborhood, the energy released could flood the surrounding space with radiation, including visible light, ultraviolet rays, and potentially dangerous gamma rays. Depending on the magnitude of the event, these bursts of energy could temporarily alter the brightness or even the color of the star, making it appear vastly different from what we normally observe. For planets orbiting a star that experiences a star quake, the impacts could be severe. A planet similar to Earth could see its atmosphere severely affected. Intense radiation could strip away atmospheric layers, altering the chemical composition of the planet's atmosphere, and possibly even triggering changes to the surface environment. Such a surge of energy could trigger planetary climate shifts, making it inhospitable for life as we know it. But the effects might not be limited to planets orbiting the quake-stricken star alone. If the energy release is particularly intense, even Earth could experience some of the fallout, as high-energy radiation could make its way across the vast expanse of space, influencing our own atmospheric conditions. Phenomena such as increased auroras, disruptions to satellite communications, and potential issues with power grids could occur, though Earth's thick atmosphere would likely offer some degree of protection. Furthermore, there is a wider concern regarding the interstellar medium, the matter that exists between stars. A powerful starquake could generate shockwaves or stellar winds that ripple through the surrounding space. These disturbances could have an impact on the formation of new stars and the gravitational dynamics of nearby star systems, highlighting the interconnectedness of cosmic phenomena. Even though starquakes are relatively rare, particularly in stars in the later stages of their evolutionary cycles, their potential to reshape the environment of their host systems and beyond speaks to the unpredictable and dynamic nature of the universe. In the grand scheme of cosmic events, one of the most spectacular occurrences is the collision of galaxy clusters, a rare and awe-inspiring event in the life of the universe. These colossal collections of galaxies, each held together by the gravitational pull of their constituent stars, gas and dark matter, are constantly on the move. As two such clusters draw closer together, they begin to interact, with the immense gravitational forces involved stirring the dark matter that permeates the cosmos. This interaction can have far-reaching effects, from the flinging of entire galaxies out of the clusters to the formation of new stars as gas clouds condense under the intense pressure created by the collision. The role of hot gas in these interactions is particularly striking. As the clusters collide, the gas within them is heated to extreme temperatures, producing a luminous plasma that emits vast amounts of energy in the form of X-rays. Astronomers using specialized telescopes can observe these emissions and map the densest and hottest regions of the clusters, providing a stunning picture of the cosmic collision in action. While galaxies themselves can often pass through one another without direct collision due to the vast distances between individual stars, the gravitational forces at play during such a merger can trigger dramatic changes. These forces cause the stars, gas, and dark matter to move in ways that fundamentally alter the structure and evolution of the clusters involved. The collision of galaxy clusters is not just a dramatic visual spectacle, it is also a powerful process that influences the broader universe. As galaxies within the clusters are thrown into new orbits or absorbed entirely, new star formations are sparked, leading to the birth of fresh stellar systems. The energetic processes at play in these collisions have the potential to drive the evolution of entire regions of space, shaping the cosmic landscape for billions of years to come. This phenomenon serves as a stark reminder of the dynamic and often violent nature of the universe, where even the largest structures are constantly in motion, colliding, merging, and evolving over vast spans of time. Such events, while rare, provide astronomers with unparalleled opportunities to study the forces that govern the cosmos on the grandest scales. As galaxy clusters merge and interact, the resulting changes offer crucial insights into the underlying principles of cosmic structure, evolution, and the nature of dark matter. This ongoing research continues to fuel our understanding of the universe, revealing its incredible complexity and the breathtaking processes that shape its ongoing development. The collision of galaxy clusters is one of the most awe-inspiring and significant events in the universe. When these immense cosmic entities collide, the process isn't merely a localized interaction. It's a spectacular transformation that ripples through the very fabric of spacetime itself. This cosmic upheaval has profound implications, not only on the galaxies involved, but also on the surrounding environment, influencing everything from star formation to the mysterious distribution of dark matter. As these celestial giants come together, they do not just merge, they reshape the cosmos in ways that scientists are only beginning to understand. During the merging process, the immense gravitational forces at play can produce gravitational waves, ripples in the fabric of space-time that spread out across the universe. These waves, though imperceptible to the human eye, are detected by advanced observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, which are designed to capture the faintest vibrations caused by these cataclysmic events. When detected, these waves offer astronomers a rare glimpse into the dynamics of galaxy cluster collisions, providing insights into the violent and complex processes at work during these cosmic events. Gravitational waves allow scientists to peer into the heart of some of the universe's most energetic and enigmatic interactions, unveiling the hidden forces shaping galaxies. Moreover, the aftermath of a galaxy cluster collision can be observed through various indirect means. One of the most fascinating phenomena resulting from such an encounter is gravitational lensing, a powerful tool used by astronomers to map the distribution of dark matter. When light from distant objects, often galaxies millions or even billions of light years away, passes through the gravitational field of a massive galaxy cluster, the light is bent and distorted. This bending effect magnifies and distorts the light, creating warped images of the background objects. Through this lens, scientists are able to observe how dark matter, which doesn't emit light but has mass and exerts gravitational influence, is distributed in and around the collision site. These observations are crucial for refining our understanding of the unseen and mysterious substance that constitutes a large portion of the universe's mass. Galaxy cluster collisions are not only dramatic in terms of their gravitational influence, but they are also a testing ground for understanding cosmic evolution. As these massive structures collide, they offer a window into how galaxies, gas, and even dark matter evolve over time. Each observation adds a layer of understanding to the broader story of cosmic history, helping us unravel the complex dynamics that shape the universe. The study of such events, from their initial stages to their eventual aftermath, is vital for scientists seeking to understand the universe's past, present, and future. These collisions represent both a violent and productive phase in the life of galaxies, sparking new star formation and altering the paths of countless stars in their wake. When two galaxies collide, the gravitational influence each exerts on the other can result in dramatic changes to their shapes. The intense gravitational tug-of-war forces gas, dust, and stars into new configurations. As these materials collide, the pressure and density increase, creating the conditions necessary for star formation. Gas clouds are compressed under the immense pressure, triggering the birth of new stars. In some cases, this process can lead to the formation of vibrant nebulae, vast glowing clouds of gas and newly formed stars that light up the surrounding space. These nebulae, often rich in hydrogen and other elements, are some of the most stunning and colorful phenomena visible in the universe. The effects of a galaxy collision extend far beyond the immediate area of the interaction. The collision can produce shock waves, much like the ripples created by a stone thrown into a calm pond, that propagate outward through the surrounding gas and dust. These shock waves have the potential to compress gas at great distances from the collision's epicenter, creating conditions that are favorable for star formation long after the galaxies have passed through each other. In some cases, these shock waves can trigger the birth of stars in distant regions of space, contributing to the growth of new stellar populations in areas that might otherwise have remained quiet and still. But the effects of a galaxy collision aren't limited to just the gas and dust. The stars themselves undergo dramatic changes. Some may be flung out of their original galaxies into intergalactic space, while others may be drawn into new orbits, altering their paths and interactions with other celestial bodies. This rearrangement of stars can lead to the formation of new star clusters, as well as the eventual destruction of older, more stable systems. These cosmic interactions are crucial for the long-term evolution of galaxies and the stars within them, contributing to the dynamic, ever-changing nature of the universe. In cases where neutron stars collide, a process far rarer and even more violent than galaxy mergers, the consequences are equally profound. When two neutron stars collide, the resulting explosion produces an intense burst of energy, known as a kilonova, which can be seen across vast distances. The explosion also generates heavy elements such as gold, platinum, and uranium, which are dispersed into space. These elements, once released, enrich the surrounding gas and dust, eventually contributing to the formation of new stars, planets, and other celestial bodies. This process, known as nucleosynthesis, is responsible for creating many of the heavy elements that make up the matter we encounter on Earth today. In addition to these effects, the collision of galaxies or neutron stars can also lead to significant changes in the distribution of dark matter. Dark matter, the elusive substance that accounts for a large portion of the universe's mass, but doesn't interact with light, is believed to be concentrated in the cores of galaxies. When galaxy clusters collide, the dark matter does not interact as strongly with the ordinary matter in the galaxies, so it tends to pass through the collision region without much disruption. However, the gravitational influence of the dark matter still plays a critical role in shaping the dynamics of the collision and the future interactions between galaxies. The redistribution of dark matter during a collision can alter the gravitational framework that governs the motion of galaxies, potentially influencing how they interact in the future. These cosmic events are not just confined to their immediate aftermath. They set off a chain reaction that affects the larger cosmic environment, influencing the formation and evolution of stars and galaxies for billions of years. As galaxies merge, the overall structure of the universe itself begins to shift, with new systems forming and old ones evolving. This dynamic process continues to shape the universe's large-scale structure, contributing to the ongoing expansion of the cosmos. Observing these cosmic events directly is often not possible. Instead, astronomers rely on indirect methods to study the aftermath of galaxy collisions and other massive cosmic events. One of the primary techniques is the observation of light and radiation emitted during these events. When two galaxies collide, the immense gravitational forces at play generate enormous amounts of energy, emitting light across a wide range of wavelengths, including visible light, radio waves, and X-rays. By using telescopes designed to detect specific wavelengths of light, astronomers can capture the data needed to piece together the details of the collision. Astronomical instruments act as our eyes and ears to the cosmos, capturing data from distant regions of space that we would otherwise be unable to perceive. By analyzing this light, scientists can infer a wealth of information about the physical conditions during and after the collision. These instruments help astronomers piece together the puzzle of galaxy cluster mergers, offering insight into the formation and evolution of galaxies, stars, and the large-scale structure of the universe itself. In addition to direct observations, astronomers use computer simulations to model these interactions in greater details. These simulations take into account the laws of physics, including gravity, hydrodynamics, and electromagnetism, as well as observational data from actual galaxy collisions. By simulating the collision of galaxy clusters or other massive objects, scientists can visualize potential outcomes, exploring different scenarios and refining their understanding of these processes. Comparing the results of simulations with actual observational data helps astronomers improve the accuracy of their models, leading to a more detailed and nuanced understanding of cosmic collisions. Another valuable tool for studying these events is gravitational lensing, which occurs when a massive object, like a galaxy cluster, passes between us and a more distant galaxy. The gravitational field of the cluster bends the light from the distant galaxy, distorting the images we receive. This bending can create multiple images of the same object, stretch its shape, or even magnify the light. By studying the effects of gravitational lensing, astronomers can gain valuable insights into the distribution of mass, including dark matter in and around galaxy clusters. These observations, combined with other data, allow scientists to unravel the secrets of cosmic collisions and explore the complex dynamics at play. The universe is not just made up of galaxies and stars. It also contains vast, nearly empty regions known as cosmic voids. These voids are enormous expanses of space where the density of matter is much lower than in the surrounding regions. They can span millions of light years across, creating a stark contrast with the dense filaments of galaxies and clusters that weave through the universe. While cosmic voids are often overlooked, they hold crucial insights into the universe's history and future. In the early universe, matter was distributed fairly evenly, but gravity began pulling matter together, forming clumps that would eventually become galaxies and clusters of galaxies. As this process unfolded, vast areas of space remained empty, giving rise to the cosmic voids we see today. The formation of these voids is still not entirely understood, and they challenge our current understanding of dark matter, dark energy, and the overall evolution of the cosmos. One of the most perplexing aspects of cosmic voids is their size. Some of these voids are so enormous that they dwarf even the largest galaxy clusters. These massive regions of emptiness have important implications for our understanding of the universe's expansion. Scientists have observed that voids influence the motion of galaxies, affecting their distribution and the rate at which the universe is expanding. Understanding the nature of these voids and the role they play in the universe's evolution remains one of the most intriguing challenges in modern cosmology. In the boundless expanse of the universe, cosmic voids emerge as one of the most perplexing and fascinating features. These vast, almost incomprehensibly empty regions offer critical insights into the deeper mechanics of the cosmos, specifically regarding the nature of dark energy, the mysterious force responsible for the accelerated expansion of the universe. By studying these enormous voids, scientists are able to unlock secrets about the universe's structure and its complex evolution, revealing more about the fundamental forces that govern its existence. The interaction between these colossal voids and the matter that permeates the rest of the universe offers a rich landscape for discovery, sparking further inquiry into the mysteries that have long eluded our understanding. Cosmic voids are, in essence, the opposite of the dense clusters of galaxies and stars that fill much of the universe. These voids are vast expanses of space where the density of matter is astonishingly low, sometimes almost non-existent compared to the surrounding regions. Imagine, if you will, these voids as colossal bubbles scattered across the fabric of space, each one a vast emptiness that seems to defy the traditional idea of how matter should be arranged. For centuries, we have been taught that the universe is a vast, homogeneous expanse where matter is evenly distributed, but the discovery of these voids has shattered that notion. Instead, the universe reveals itself as a highly organized and intricate structure, with galaxies and galaxy clusters forming along long, thread-like filaments that trace the boundaries of these enormous voids. The study of cosmic voids necessitates a shift in perspective. While these voids might seem empty at first glance, their significance cannot be overstated. Despite their lack of matter, they occupy a significant portion of the universe's total volume. In fact, the vast majority of the universe is composed of these low-density voids, yet they contribute only a tiny fraction of the universe's total mass. This discrepancy between volume and mass forces astronomers to rethink traditional models of cosmic distribution, especially when considering the behavior of galaxies. It becomes clear that galaxies do not cluster around denser regions alone. They also tend to congregate around the edges of these enormous voids, creating an intricate and sometimes surprising arrangement of matter throughout the universe. However, the importance of cosmic voids extends far beyond their physical dimensions. They play an essential role in the ongoing evolution of the universe. These regions of emptiness are not static. They influence the movement and behavior of galaxies, and in turn, help shape the development of larger cosmic structures. The dynamics within these voids, particularly the interactions between galaxies and the fabric of space itself, hold the key to understanding how structures in the universe grow and evolve over time. Moreover, voids offer a unique window into the behaviors of dark matter and dark energy, two of the most enigmatic components of the universe that continue to defy full explanation. Dark matter, which does not emit or interact with light, is believed to make up a significant portion of the universe's total mass. Its presence is inferred through gravitational effects, such as the way it bends light around massive objects or alters the motion of galaxies. The voids, with their low density, offer an intriguing opportunity to study how dark matter influences the universe's evolution. By examining how galaxies behave near the edges of voids, researchers can gain valuable insights into how dark matter is distributed throughout the universe and how it interacts with visible matter. Similarly, voids may help scientists probe the nature of dark energy, the mysterious force accelerating the expansion of the universe. By studying the behavior of galaxies within these voids, astronomers hope to uncover clues about the role dark energy plays in shaping the universe's future. Beyond their association with dark matter and dark energy, cosmic voids are also central to understanding the broader structure of the universe. These voids are not mere gaps in space. They are integral to the larger cosmic web that underpins the universe's architecture. The web-like distribution of galaxies, with voids acting as the spaces between clusters, forms a highly complex and structured pattern that is fundamental to the universe's overall design. The study of voids offers scientists a clearer picture of the cosmic architecture and how it has evolved over billions of years. This intricate structure, with its galaxies, clusters, and voids, provides the scaffolding upon which the universe's larger-scale evolution is built. The exact origins and evolution of these cosmic voids remain one of the universe's great mysteries. It is widely believed that the universe's expansion, which began after the Big Bang, played a crucial role in creating these voids. As the universe expanded, Gravitational forces caused some regions to become less populated with matter, forming vast empty zones. However, the specific processes by which these voids are created and how they evolve over time are still not entirely understood. Researchers are actively investigating how these voids interact with their surrounding structures, such as galaxies and clusters, and whether they play a role in phenomena like star formation or galaxy evolution within their bounds. In addition to their role in the evolution of the universe, cosmic voids are also crucial to answering some of the most fundamental questions in cosmology. The study of voids can help researchers determine the overall geometry of the universe and its fate. Given that voids are regions of space with lower than average density, they offer a natural laboratory for studying how the universe will continue to evolve. Will the universe continue to expand indefinitely, driven by the mysterious force of dark energy? Or will it eventually collapse under its own gravitational pull, leading to a big crunch? Or will it settle into a steady state, with the expansion slowing down over time? These are questions that researchers hope to answer by studying the behavior of cosmic voids and the way they interact with other elements of the cosmic structure. Cosmic voids, therefore, are far from empty. They are teeming with hidden information and offer a rich field of scientific inquiry. Their study not only helps us understand the past and present of the universe, but also provides clues about its future. These voids are intimately connected with the forces that shape the universe's structure, from the formation of galaxies and stars to the dynamics of dark matter and dark energy. By delving into the mysteries of cosmic voids, scientists are able to refine existing models of the universe's evolution and push the boundaries of our understanding even further. Dark matter, often referred to as the unseen mass of the universe, plays a critical role in the formation of cosmic structures. After the Big Bang, the early universe was a hot, dense soup of particles. As it expanded and cooled, matter began to clump together under the influence of gravity. However, the vast majority of matter in the universe is invisible to us. Ordinary matter, the kind that makes up stars, planets, and galaxies, constitutes only a small fraction of the universe's total mass. The rest is believed to be made up of dark matter, which does not interact with light but still exerts a gravitational pull on visible matter. This invisible mass was instrumental in the formation of the large-scale structures we observe today, as dark matter's gravitational influence guided the formation of galaxies and galaxy clusters. The evidence for dark matter's existence comes from several sources. One of the most compelling pieces of evidence comes from the rotation of galaxies. According to our current understanding of gravity, the speed at which stars orbit the center of a galaxy should decrease with distance from the center. However, observations show that stars on the outer edges of galaxies are moving much faster than expected. This discrepancy suggests that there is far more mass in these galaxies than we can account for with visible matter alone, leading scientists to conclude that an invisible form of matter, dark matter, is present. Another key piece of evidence comes from the phenomenon of gravitational lensing, where light from distant objects is bent as it passes through massive foreground objects. By analyzing how light is distorted in this way, astronomers can infer the presence of unseen mass in the foreground, which corresponds to dark matter's predicted distribution across the universe. In conclusion, cosmic voids are not just empty regions of space. They are critical to understanding the universe's structure, evolution, and the forces that shape it. These vast emptinesses provide a wealth of information about dark energy, dark matter, and the fundamental processes that govern the cosmos. By exploring these voids, astronomers are pushing the boundaries of our knowledge, uncovering new insights into the nature of the universe itself, and charting a path toward a deeper understanding of the cosmos. In the vast expanse of the universe, there are invisible forces at work, forces that shape the cosmos in ways that remain largely hidden from direct observation. Among these enigmatic forces are dark matter and black holes, two phenomena whose presence and influence extend far beyond our ability to directly perceive them. Yet, through the lens of advanced simulations and increasingly sensitive observational tools, scientists have begun to uncover the profound impact that these invisible structures have on the formation, evolution, and behavior of the universe. When simulations of cosmic evolution incorporate dark matter, the results align closely with the observed distribution of galaxies and galaxy clusters, providing compelling evidence for its existence and influence. Without dark matter, the universe's structure would be entirely different. Simulations that exclude it fail to replicate the actual cosmic landscape, reinforcing the idea that this unseen substance plays a crucial role in the architecture of our universe. It is not just a theory, it is an integral part of how the cosmos came to be and how it continues to evolve. Dark matter, though invisible, makes up a significant portion of the universe's mass. Despite its elusive nature, it exerts a powerful influence on the motion of galaxies. In fact, without dark matter, galaxies would not have the necessary gravitational binding to remain intact. Galaxies would drift apart in a cosmic disarray, unable to form stable structures. This disruption would not only impact the galaxies themselves, but also affect the conditions required for star formation. Stars would struggle to form, and the intricate balance that allows life to emerge could be permanently altered. In a universe without dark matter, the basic framework for the existence of stars, and by extension life, would be drastically different. Similarly, black holes represent another mysterious component of the universe. These celestial objects are the most extreme gravitational environments known to science. Their immense mass warps space-time, creating profound effects on the surrounding space. Black holes are not merely passive entities. They actively consume nearby stars, gas, and other matter, and in doing so, release powerful bursts of radiation. This radiation can dramatically alter the environments around them, affecting nearby celestial bodies in unpredictable ways. The fierce gravitational pull of a black hole can tear apart stars, drawing them into the singularity, where the laws of physics as we know them break down. In some cases, black holes may even trigger the violent explosion of supernovae, which can ignite a chain reaction in the surrounding space. These cosmic events, whether they involve black holes, supernovae, or other cataclysmic processes, have far-reaching consequences for the behavior of other celestial bodies in the vicinity. When galaxies collide or merge, the gravitational forces at play can lead to extraordinary phenomena, such as the emission of gravitational waves. Gravitational waves are ripples in the fabric of space-time, produced by the most energetic and violent processes in the universe. These waves are capable of traveling across vast distances, carrying with them information about the events that caused them. For example, when black holes or neutron stars collide, the resulting gravitational waves provide valuable insights into the masses, spins, and behaviors of these celestial objects. Gravitational waves, though invisible to traditional telescopes, offer a new and revolutionary way to study the universe. They allow scientists to detect events that would otherwise be completely undetectable, providing a new window into the most violent and energetic processes occurring in the cosmos. The collision of two black holes, for instance, sends out powerful gravitational waves that carry with them detailed information about the event. By detecting these waves, scientists can study phenomena that were once completely beyond our reach. The detection of gravitational waves has confirmed key aspects of Einstein's theory of general relativity, while also revealing previously unknown objects, such as binary black hole systems, that had never been observed before. Gravitational waves thus open up an entirely new dimension of cosmic exploration. They represent not only a new way of observing the universe, but also a new way of understanding the fundamental nature of space and time. By studying these ripples in space-time, scientists can probe the universe at its most extreme, uncovering secrets about the most violent and energetic events that have shaped the cosmos. This new field of study, known as gravitational wave astronomy, complements traditional astronomy by providing a deeper, more comprehensive understanding of the universe's most mysterious phenomena. However, the influence of dark matter and black holes extends far beyond individual cosmic events. The distribution of dark matter within a galaxy plays a crucial role in shaping its structure and dynamics. Imagine dark matter as an invisible scaffold, holding the galaxy together by providing the necessary gravitational support for stars, gas, and dust. If the configuration of dark matter were to change, the consequences would be profound. One potential effect could be on the orbits of stars and other celestial bodies within the galaxy. Currently, stars in the Milky Way follow stable paths thanks to the gravitational pull of dark matter. If dark matter were to become more concentrated in some regions or dissipate in others, the gravitational balance of the galaxy would be disrupted. This could cause stars to accelerate, slow down, or even be flung from their expected orbits, leading to chaotic motion within the galaxy. Moreover, changes in the distribution of dark matter could have significant effects on the formation of new stars. Dark matter plays a key role in pulling ordinary matter together, providing the gravitational pull that leads to the formation of stars. If the density of dark matter in certain regions were to decrease, the gravitational pull would weaken, potentially resulting in fewer regions where stars could ignite. Conversely, if dark matter became more concentrated in certain areas, it could trigger a surge in star formation, leading to the creation of a burst of new stars in those regions. These shifts in dark matter distribution could also influence the interactions between galaxies. When galaxies come into close proximity, the gravitational forces between them can lead to tidal interactions, causing the exchange of stars or gas between the galaxies. This process can alter the shapes and contents of the galaxies involved, further illustrating the interconnectedness of these cosmic structures. The Milky Way's dynamics, for example, are deeply influenced by the distribution of dark matter. A change in the distribution of this invisible substance could ripple through the galaxy, affecting everything from the orbits of stars to the overall shape and stability of the galaxy itself. These invisible forces, the dark matter that holds galaxies together, the black holes that warp space and time, and the gravitational waves that carry information across the universe, are not just abstract concepts. They are the very forces that shape the universe we live in. They govern the formation, evolution, and eventual fate of galaxies, stars, and all other celestial bodies. Their effects extend to every corner of the cosmos, constantly reshaping the universe through violent encounters and cataclysmic events. The study of these phenomena is more than just an academic pursuit. It is a journey into the very heart of the universe's most profound mysteries. As we continue to explore these unseen structures, we are uncovering a deeper, more complex layer of reality, one that is hidden from plain sight, but whose influence is felt in every corner of the cosmos. The discovery and detection of gravitational waves has opened a new chapter in our exploration of the universe, one where the boundaries of human knowledge are constantly being tested and pushed to their limits. With every new wave that is detected, we are not just witnessing celestial events unfold across the cosmos, but we are also confronting the fundamental limits of our understanding of physics. As these waves ripple through space-time, they carry with them a wealth of information that challenges our existing theories, especially when the predictions of general relativity, the theory that describes the force of gravity, don't quite match up with what we observe in the universe. These discrepancies are not merely points of contention. They are golden opportunities to uncover new scientific principles, potentially rewriting how we understand everything from the nature of gravity to the very fabric of space and time itself. The phenomena of gravitational waves have already served some of the most essential aspects of Albert Einstein's theories, but they also point to a wealth of mysteries that remain unsolved. Among these are the dark forces that shape our universe, dark matter, and dark energy. While these concepts have been the subject of theoretical work for decades, their true nature remains a profound mystery. Could the study of gravitational waves offer the key to unlocking these dark components of the universe? Perhaps the detection of these waves could guide us toward understanding whether dark matter and dark energy are mere theoretical constructs, or whether they are tangible, real phenomena that can be directly observed and measured. Gravitational wave research has ushered in a revolutionary era in astrophysics. This new field of study not only allows us to observe the most violent and enigmatic events in the cosmos, events that often involve the collision of massive celestial bodies, but it also offers a way to enhance our understanding of the underlying physical laws that govern the universe. With each new detection, scientists gain an increasingly detailed picture of the forces that shape the cosmos. The gravitational waves that travel across the universe are like whispers from the farthest reaches of space, carrying with them evidence of cataclysmic events that occurred billions of years ago. These events may have originated in places too far to observe with traditional telescopes, but through the study of gravitational waves, we can peer into these regions of the universe and glimpse phenomena that were previously beyond our reach. The potential applications of gravitational wave research are vast and profound. For instance, by studying the gravitational waves emitted by colliding black holes or neutron stars, researchers can investigate the properties of these objects in unprecedented detail. This could offer critical insights into the behavior of matter under extreme conditions, as well as the nature of space-time itself. More importantly, this research could provide answers to some of the most fundamental questions about the universe, questions about the very forces that govern its creation and evolution. Gravitational waves could, for example, help us better understand the rapid expansion of the universe in its earliest moments, right after the Big Bang. By studying these waves, scientists hope to uncover details about the forces that shape the universe in its infancy, offering a clearer picture of its birth and evolution. Furthermore, the detection of gravitational waves could also help scientists investigate the mysteries surrounding dark matter and dark energy. These unseen entities are believed to account for a significant portion of the universe's mass and energy, yet their existence and nature remain elusive. Gravitational waves could provide a unique lens through which to study these components, shedding light on whether they are simply abstract theoretical concepts or real physical entities that exert tangible influence on the universe. As gravitational wave research continues to evolve, it may ultimately reveal whether these enigmatic forces are a fundamental part of the cosmos or merely a figment of our theoretical models. Beyond the basic study of gravitational waves, the field is also benefiting from a new approach that combines multiple types of observational data. By using what's known as a multi-messenger approach, scientists can combine gravitational wave data with electromagnetic signals such as light or gamma rays that are emitted by the same cosmic events. This method allows researchers to build a more complete picture of what's happening in distant parts of the universe. For example, when neutrons collide, they not only emit gravitational waves, but also produce bright flashes of light and other forms of radiation. By studying both the gravitational waves and the light emitted during these events, scientists can learn about how heavy elements are formed in such cataclysmic collisions. These elements, which include the very building blocks of life on Earth, could have been formed in these cosmic collisions, offering new insights into the origins of the elements that make up our world. The future of gravitational wave research is not just about observing what already exists in the universe. It is about transforming our understanding of cosmic events entirely. Every new discovery has the potential to challenge our existing theories, encouraging the development of new models and inspiring the creation of groundbreaking technologies. As scientists continue to listen for these faint whispers from the universe, they are uncovering a richer, more detailed narrative of the cosmos, one that addresses some of the most fundamental questions in science. With each new wave detected, we are not just expanding our understanding of the universe, we are rewriting the very laws that govern its behavior. In addition to the breakthroughs provided by gravitational wave astronomy, another dramatic and visually striking cosmic event is the tidal disruption event, which occurs when a star ventures too close to a supermassive black hole. Imagine a star, a massive ball of gas and light, moving through the universe, bound together by its own gravity. As the star approaches a black hole, however, its gravity becomes overwhelmed by the black hole's far stronger gravitational pull. The force that the black hole exerts on the star is not uniform. It is stronger on the side of the star nearest to the black hole and weaker on the side farthest away. This difference in gravitational forces creates what are known as tidal forces, much like the forces the moon exerts on Earth's oceans, but on a much more violent and destructive scale. These tidal forces stretch and compress the star to such an extent that the star can no longer maintain its structure. The result is the star's disintegration. As the star is torn apart, some of its material is drawn into the black hole, while other parts are flung outward at incredible speeds. These ejected fragments create stunning displays of light and energy as the material interacts with the surrounding space. The process of the star's destruction and the subsequent accretion of its material into the black hole creates powerful bursts of radiation, which can be detected by astronomers from vast distances. These tidal disruption events, therefore, serve as one of the most visually spectacular phenomena in the universe. The study of tidal disruption events provides astronomers with valuable insights into the behavior of supermassive black holes and the life cycles of stars. As part of the ongoing effort to explore these distant and extreme events, scientists have developed an array of powerful tools and techniques for studying the farthest reaches of the universe. One of the most crucial tools in this endeavor is the telescope. There are many different types of telescopes used in this research, ranging from ground-based instruments to space-based observatories. Ground-based telescopes use large mirrors to collect and focus light from distant objects in the universe, capturing their image in optical wavelengths. However, the Earth's atmosphere can distort this light, making it difficult to observe celestial phenomena accurately. To overcome this challenge, astronomers have also deployed space-based telescopes, which orbit high above the Earth's surface, allowing them to observe the universe without the interference of the atmosphere. Yet, light is not the only tool in an astronomer's arsenal. The universe emits a broad spectrum of electromagnetic radiation, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each of these types of radiation provides a different view of the cosmos, revealing unique aspects of celestial phenomena. For example, events such as supernova explosions or the activities of black holes can produce X-rays, which can only be detected by telescopes placed in space. By studying these different forms of electromagnetic radiation, scientists can gain a deeper understanding of the objects and events they observe. The sheer volume of data collected by these instruments requires sophisticated analysis techniques to interpret. Vast amounts of information are processed using powerful algorithms and computer models, allowing researchers to reconstruct the physical conditions of distant regions of space. This information can reveal crucial details about the composition, temperature, distance, and velocity of celestial objects, which help scientists understand their properties and behavior. Collaboration plays a key role in these efforts. International partnerships among scientists from various fields of study facilitate the sharing of knowledge and resources. By pooling their expertise and data from multiple telescopes, both ground-based and space-based, scientists can create a more comprehensive understanding of cosmic events. Through these combined efforts, we are slowly piecing together a more complete picture of the universe, one that continues to reveal its awe-inspiring mysteries. While the vastness of space can sometimes seem overwhelming, human ingenuity and technological advancements are allowing us to pierce through the darkness. With each new discovery, we continue to unlock the secrets of the cosmos, and the universe becomes a little less mysterious. Through the continued study of gravitational waves, tidal disruption events, and other cosmic phenomena, we are expanding our understanding of the universe, not just as it exists today, but as it has existed throughout time. The future of astrophysics holds even greater promise, and as we continue to listen to the whispers of the universe, we inch closer to understanding the profound forces that govern everything from the smallest particles to the largest cosmic structures. Moreover, the study of black holes fundamentally challenges our most established scientific theories, particularly those concerning the nature of gravity and quantum mechanics. The intriguing paradox begins when matter or light crosses the event horizon of a black hole, as this boundary seems to swallow everything, appearing to remove it entirely from our universe. This raises profoundly unsettling questions about the very fabric of reality itself. If nothing can escape a black hole, what does that imply for the laws of physics we rely on? The idea that anything could truly be lost forever contradicts our understanding of conservation in physics, especially information conservation. In an attempt to resolve this paradox, renowned physicist Stephen Hawking proposed an extraordinary theory that black holes might not be entirely permanent. His hypothesis, known as Hawking radiation, suggests that black holes could slowly evaporate over time by emitting tiny amounts of radiation, eventually losing mass and possibly even disappearing. This radical suggestion offers the tantalizing possibility that black holes might eventually leak information back into the universe, contradicting the traditional notion that once information falls into a black hole, it is gone forever. This phenomenon has sparked what is known as the information paradox, a core mystery in modern physics that continues to provoke intense debate. What truly happens to the information, be it the matter or the data it contained, that falls beyond a black hole's event horizon? Beyond these theoretical quandaries, the direct observation of black holes, especially those located at the centers of galaxies, provides us with unique insights into their profound influence on cosmic evolution. The behavior of these massive cosmic objects offers a window into understanding how galaxies form, grow, and evolve. We now know that black holes play an active role in shaping the universe, directly influencing processes like star formation and the overall dynamics within galaxies. This reshapes our view of black holes, not as passive, empty voids, but as pivotal agents in the ongoing transformation of the cosmos. Each exploration into the behavior and properties of black holes continues to expand our knowledge of fundamental physics, revealing startling truths about the nature of time and space. These findings reveal intricate connections within the fabric of the cosmos, stretching across scales from the quantum to the cosmological. As we continue to peel back the layers of mystery surrounding black holes, they remain a crucial key to unlocking the deepest, most fundamental truths about the universe we inhabit. In a similar vein, quasars stand as some of the most luminous and energetic objects we have ever observed. These distant phenomena, powered by supermassive black holes located at the centers of galaxies, are capable of emitting vast amounts of energy. As material, gas, and dust spirals into these black holes, it forms an accretion disk. This swirling disk of hot ionized material reaches incredibly high temperatures, emitting radiant energy across the electromagnetic spectrum, from radio waves all the way to visible light. The energy emitted by quasars can far outshine the collective light of the stars in the entire galaxy they reside in, making them some of the brightest objects in the observable universe. One of the most captivating aspects of quasars is the jets of particles they emit. These narrow, high-speed streams of particles are ejected from the poles of the black hole's accretion disk at nearly the speed of light. These jets, driven by intense magnetic fields generated by the accretion disk, stretch across vast distances, sometimes even exceeding the size of the host galaxy itself. To visualize this, imagine a blender in action. As ingredients spin rapidly within the blender, some are ejected outward from the center, mirroring the way material is expelled along the jets of a quasar. The sheer power and scale of these jets are extraordinary. Some extend for thousands of light years, carrying more energy than entire galaxies. This energy drives shockwaves that propagate through the intergalactic medium, influencing star formation in their wake. The impact of quasar jets goes far beyond their immediate environment. These powerful jets can regulate the formation of stars within their host galaxy. As a jet collides with the surrounding gas, it can trigger shockwaves, compressing gas and leading to the birth of new stars. However, the process is more complex. The energy from these jets can also heat up the interstellar medium to such an extent that it prevents further star formation. This dual effect, both fostering and inhibiting star birth, illustrates the complex role that quasars play in the evolution of galaxies. As the jets extend far beyond their host galaxy, they influence the broader intergalactic medium. The material expelled by these jets enriches the space between galaxies with heavy elements produced by the death of stars. This process is crucial for the chemical evolution of the universe, affecting galaxy formation and the development of larger cosmic structures. The energy carried by these jets also plays a role in regulating the temperature and density of the gas between galaxies, influencing how galaxies cluster together and evolve over time. In essence, quasar jets serve as dynamic agents of change in the universe. They are not simply extraordinary cosmic phenomena, They are active participants in the ongoing evolution of galaxies and the vast expanses of space beyond. The study of quasars, and especially their jets, also offers valuable insight into the early universe. As these energetic phenomena can be observed billions of light years away, they provide a snapshot of the universe in its youth, offering critical information about how galaxies evolved in the first few billion years after the Big Bang. This makes quasars vital tools in cosmology, allowing scientists to probe the distant past and better understand the processes that shape the universe as we know it today. Quasar jets are a testament to the extreme energy and forces at play in the universe. As material spirals into the supermassive black hole at the center of a quasar, it generates an accretion disk that heats up to extraordinary temperatures, releasing immense amounts of radiation. The powerful jets that emerge from these disks travel vast distances, producing electromagnetic radiation across many wavelengths, from radio waves to X-rays. These jets can even surpass the brightness of the entire galaxy, making quasars some of the most luminous objects in the universe. Yet, despite our growing understanding of how quasars form, many aspects of these phenomena remain mysterious. One major question is the exact mechanism by which the jets are launched and focused into narrow beams. While it is believed that the rotation of the black hole plays a crucial role, the interactions between the magnetic fields in the accretion disk and the surrounding environment are still not fully understood. Furthermore, the impact of quasar jets on their host galaxies remains an area of intense study. How do these jets affect star formation within their galaxies? What happens to the material that the jets interact with? Given that quasars can be observed from such great distances, they offer a unique perspective into the evolution of galaxies, providing clues to how these systems have evolved over billions of years. As observational technologies improve, scientists hope to uncover more secrets about these extraordinary cosmic objects. The insights gained from studying quasars and their jets will not only help us better understand the nature of black holes, but also provide crucial information about the evolution of galaxies, the formation of stars, and the larger structure of the universe. Wormholes, another fascinating theoretical concept in the realm of astrophysics, represent potential shortcuts through the fabric of spacetime. Imagine spacetime as a vast, two-dimensional sheet that contains all points in the universe. Under normal conditions, traveling from one point to another across vast distances would require traversing the entire sheet. However, a wormhole would theoretically fold this sheet, connecting two distant points through a tunnel-like structure. This would allow for instant travel between these 2 points, bypassing the usual vast distances that separate them. Despite their alluring potential, wormholes come with a number of theoretical risks and uncertainties. Chief among these concerns is the stability of the wormhole itself. For a wormhole to remain open, it is theorized that a special type of exotic matter which possesses negative energy density would be required. This exotic matter is purely hypothetical and has never been observed, making the existence of stable wormholes a subject of intense debate. If such matter could exist, it might allow wormholes to remain open, but the nature of this material remains one of the biggest mysteries in modern physics. The concept of wormholes, long a subject of fascination and intrigue in both scientific circles and popular imagination, is one that carries with it as much promise as it does peril. These hypothetical passages through space and time, often likened to cosmic shortcuts, could, in theory, allow for instantaneous travel between distant regions of the universe. However, the mere possibility of navigating such phenomena raises profound concerns, primarily because of the unpredictable and largely unknown nature of such a journey. If, by some miracle, someone were to attempt traveling through a wormhole, there would be a significant risk of encountering extreme gravitational forces, potentially stretching or compressing the traveler in ways that defy comprehension. This phenomenon, often referred to as spedification, occurs when an object is subjected to such immense gravitational forces that it is elongated or torn apart, similar to how a strand of spaghetti might be pulled and stretched. The effect could prove to be fatal, with travelers being destroyed long before reaching the other side, thus highlighting one of the most pressing concerns regarding the practicality of wormhole travel. Additionally, the potential consequences for causality, a fundamental principle that dictates the relationship between cause and effect, are even more alarming. Causality, as we understand it, forms the backbone of reality itself. A violation of this principle could unravel the very fabric of the universe. Traveling through a wormhole might create paradoxes where a person could, in theory, arrive in the past, potentially altering the course of events in a way that contradicts established history. Imagine a scenario where an individual travels back in time and by accident or intention prevents key historical events from unfolding. Such a situation would give rise to a host of existential and philosophical questions about the true nature of time, reality, and the potential fragility of the universe itself. This concept, often explored in science fiction, is not merely a fictional construct, but a theoretical dilemma that scientists and philosophers continue to debate. The idea of wormholes, despite their intriguing possibilities, is deeply enmeshed in the complexities of general relativity, a cornerstone theory developed by Albert Einstein. General relativity posits that massive objects such as stars and planets warp the very fabric of space-time around them. This warping, akin to the way a heavy ball deforms a trampoline, is central to our understanding of gravity. It is in this distorted space-time that some scientists propose the existence of wormholes, tunnels through the fabric of space-time that could, in theory, connect two distant points in the universe, offering shortcuts that bypass the vast distances normally required for interstellar travel. One of the primary pieces of evidence supporting the existence of wormholes comes from the mathematics inherent in general relativity. The equations derived from this theory allow for solutions that mathematically describe wormholes as theoretical constructs. However, as elegant and coherent as these mathematical solutions may be, they do not guarantee that wormholes actually exist in the physical world. This uncertainty points to a critical challenge in modern physics: the transition from theoretical models to empirical evidence. In order for wormholes to be realized as actual phenomena, it is believed that a mysterious substance known as exotic matter would be required to stabilize the wormhole and keep it open. Exotic matter, which is theorized to possess negative energy density, would serve to counteract the immense gravitational forces that would otherwise cause a wormhole to collapse upon itself. Without this exotic matter, a wormhole would likely fold in on itself, rendering it impassable. While no direct evidence of wormholes has yet been discovered, recent advancements in observational technologies and theoretical physics are beginning to open up new avenues for exploration. One breakthrough, for instance, has been the detection of gravitational waves, ripples in space-time that occur when massive objects like black holes merge. These waves, first predicted by Einstein's theory, have been observed and measured by instruments like LIGO, leading to fresh perspectives on the structure and behavior of space-time itself. Some scientists speculate that if wormholes do exist, they might be detectable through similar gravitational wave signals or other anomalies in space-time. Furthermore, the study of quantum particles, entities that behave in strange and often non-intuitive ways, has also given rise to theories that suggest there may be deep connections between the quantum world and the bizarre phenomena that wormholes represent. These connections remain speculative at best, yet they continue to capture the imagination of both physicists and laypeople alike. In parallel with these theoretical explorations, the idea of wormholes raises fundamental questions about the very nature of the cosmos. Could the universe contain hidden passages that link distant galaxies or even different regions of our own galaxy? What if these wormholes are not just theoretical curiosities, but actual physical structures waiting to be discovered? Such questions fuel the ongoing pursuit of knowledge as scientists strive to unravel the mysteries of the universe, inching ever closer to understanding the full potential of space-time and its hidden dimensions. Yet, despite the theoretical allure of wormholes, the risks they entail, particularly the potential dangers to anyone attempting to traverse them, serve as a sobering reminder of the profound uncertainties that still lie ahead in our journey to understand the universe. The implications of a wormhole existing in or near our galaxy are as profound as they are complex. One of the first concerns that arise is the issue of stability. Many theorized wormholes may in fact be inherently unstable, collapsing before anything, let alone a human traveler, could pass through. This raises the question of whether a stable wormhole could ever be formed or sustained long enough for meaningful travel. Even if such a wormhole could be stabilized, the journey itself might expose travelers to gravitational forces and phenomena that are completely unpredictable. The distortions in space-time near a wormhole could cause strange and potentially lethal effects on both the traveler and the spacecraft. Furthermore, the mere presence of a wormhole could have profound effects on the surrounding region, potentially altering the orbits of nearby celestial bodies or triggering other catastrophic events in distant parts of the galaxy. Another significant concern is the technological challenge posed by wormholes. In order to maintain a wormhole's stability, it may be necessary to harness or create exotic matter, an incredibly elusive and theoretical substance that has yet to be observed in nature. Even if we could produce this exotic matter, the methods of manipulating it to achieve practical results remain entirely unknown. The implications of these challenges are not limited to space travel. The ability to create or control a wormhole could radically alter the dynamics of communication, trade, and interaction between civilizations, both on Earth and beyond. The dream of wormholes, in this sense, intertwines the excitement of cosmic exploration with the weight of responsibility. The potential to instantaneously travel vast distances could usher in a new era of human achievement, but it could also bring about unforeseen consequences, including the misuse of this powerful technology. Beyond the realm of wormholes, the universe harbors other mind-boggling phenomena that further complicate our understanding of the cosmos. One such phenomenon is antimatter, an exotic substance that behaves in a way that is the exact opposite of ordinary matter. To understand the uniqueness of antimatter, it is important to first define what it is. Antimatter consists of particles that have the same mass as regular matter, but opposite electrical charges. When matter and antimatter come into contact, they annihilate each other in a burst of energy, producing a release of energy that far exceeds the amount generated by conventional nuclear reactions. In an antimatter explosion, the energy released would be orders of magnitude greater than that of a typical supernova or thermonuclear explosion, making it one of the most powerful processes known to science. The energy produced in an antimatter explosion is derived from the complete conversion of mass into energy in accordance with Einstein's famous equation, E equals mc squared. This relationship demonstrates that even tiny amounts of antimatter could release an enormous amount of energy, equivalent to the annihilation of those particles multiplied by the speed of light squared. In comparison, conventional cosmic explosions like supernovae are the result of nuclear fusion reactions, which, while energetic, do not compare to the sheer magnitude of energy produced by antimatter. In an antimatter explosion, the energy would be released almost instantaneously without the ejection of debris. Instead of a cloud of material, an antimatter explosion would result in a brilliant flash of radiation and heat, capable of devastating entire regions of space. The efficiency of energy conversion in an antimatter explosion makes it a particularly intriguing and terrifying phenomenon in astrophysics. Despite the theoretical understanding of antimatter, its existence in nature remains elusive. While scientists have observed antimatter in cosmic phenomena, such as gamma-ray bursts and cosmic rays, direct evidence of antimatter encounters is rare and difficult to obtain. Gamma-ray bursts, one of the most powerful and energetic phenomena in the universe, are believed to occur during the collapse of massive stars or the formation of neutron stars. It is during these explosive events that matter and antimatter may interact, releasing vast amounts of energy in the form of gamma rays. In addition, studies of cosmic rays, high-energy particles traveling through space, have revealed the presence of positrons, the antimatter counterparts of electrons. These positrons, while not definitive proof of antimatter's prevalence in the cosmos, suggest that antimatter could play a larger role in the universe's most energetic events than previously thought. Ultimately, the study of wormholes, antimatter, and other extraordinary cosmic phenomena challenges the boundaries of human knowledge and invites us to reconsider our place in the universe. What we once viewed as science fiction may, in fact, contain elements of truth, awaiting discovery in the unexplored corners of space-time. As science progresses, the mysteries of the cosmos continue to unfold, offering tantalizing glimpses into the unknown and pushing the limits of our understanding ever further. The universe is filled with numerous phenomena that challenge our understanding of the fundamental laws of physics, and one of the most intriguing is the concept of antimatter. In the vastness of space, we often encounter phenomena like the Van Allen radiation belts, which hold charged particles trapped by Earth's magnetic field. These belts, when observed in conjunction with advanced gamma-ray telescopes, sometimes reveal traces of antimatter. Although the direct presence of antimatter is rare, certain observations suggest bursts of radiation that align with theoretical models, indicating that antimatter may indeed exist in these regions, albeit in ways we are only beginning to comprehend. Antimatter is a mysterious counterpart to the matter we encounter every day. It exists as a mirror image of regular matter with opposite charges, and when the two meet, they annihilate one another in a burst of energy. This energetic collision is one of the most fundamental interactions in the universe, governed by the very laws of physics. Despite its fundamental role, antimatter is a rare and elusive component in the cosmic story. While the universe is predominantly made up of matter, traces of antimatter, if they exist, could provide us with significant insights into the formation of the cosmos. These regions of antimatter might exhibit unusual interactions at their boundaries, producing distinctive gamma-ray emissions that could be detectable by space telescopes. Yet, despite these tantalizing clues, direct evidence of antimatter explosions or interactions remains just beyond our reach. One of the most exciting areas of study in the search for antimatter revolves around primordial antimatter, the antimatter that could have been created during the Big Bang, the cataclysmic event that gave birth to the universe. The universe as we know it is dominated by matter, and the question of why antimatter is so scarce remains a profound mystery in modern physics. Some cosmologists speculate that antimatter may exist in hidden pockets throughout the universe, but these regions could be rare and difficult to detect. More importantly, these pockets could be on the verge of annihilation, as any encounter between matter and antimatter would lead to mutual destruction. The search for primordial antimatter and the mysterious regions where it may exist is an exciting avenue for scientific exploration. Theoretical models predict that such regions could produce bursts of gamma-ray emissions, signaling the interaction between antimatter and matter. These emissions could be detected by advanced space-based telescopes, which are capable of observing distant and faint cosmic phenomena. Gamma-ray telescopes have already provided insights into some of the most enigmatic events in the universe, including the mysterious gamma-ray bursts that are thought to be linked to the death throes of massive stars. These bursts could be related to antimatter interactions, further adding to the intrigue surrounding antimatter's role in the cosmic narrative. However, the direct detection of antimatter in these bursts or other cosmic phenomena remains elusive. Despite this, each new observation and discovery brings scientists closer to unraveling the mysteries of antimatter as they search for evidence of its existence and examine how it fits into the broader framework of the universe's history. One of the central challenges in understanding antimatter lies in the asymmetry between matter and antimatter, a fundamental issue that arose during the very early moments of the universe. According to theoretical models, when the universe was formed in the aftermath of the Big Bang, it should have produced equal amounts of matter and antimatter. However, for reasons that remain poorly understood, a slight excess of matter emerged, leaving antimatter in relative scarcity. This imbalance between matter and antimatter is one of the most pressing questions in cosmology and particle physics. Theoretically, if the universe had contained equal amounts of both matter and antimatter, they would have annihilated each other in a burst of energy, leaving only radiation behind. Instead, the slight excess of matter that survived the annihilation process eventually formed the stars, galaxies, and all of the visible universe we see today. This matter-antimatter asymmetry is not only a fundamental puzzle, but also one of the most important unresolved issues in modern physics. If antimatter is so readily annihilated upon contact with matter, it would be incredibly difficult for antimatter to remain stable in the universe. Any localized pockets of antimatter would quickly be consumed by surrounding matter, disappearing almost as quickly as they appeared. This makes it unlikely that significant amounts of antimatter could exist in regions of space where we might expect to find it. Instead, antimatter remains one of the most elusive and difficult substances to study in the cosmos. In addition to the cosmic asymmetry, there are several other challenges that scientists face when it comes to producing and storing antimatter. While laboratories on Earth can create small amounts of antimatter in high-energy particle accelerators, these quantities are minuscule, and the energy required to produce them is immense. Producing even a fraction of a gram of antimatter would require vast amounts of energy, far beyond what we can currently generate. Moreover, the process of creating antimatter is highly inefficient. When high-energy particles collide, they sometimes create antimatter, but this antimatter is typically produced alongside large amounts of matter, meaning that the antimatter produced is quickly neutralized by the surrounding matter. The challenges do not end there. Storing antimatter is another significant obstacle, as antimatter cannot come into direct contact with regular matter without annihilating. In order to store antimatter, scientists use sophisticated technologies, including magnetic fields, to isolate the antimatter and prevent it from coming into contact with any material that would cause it to annihilate. These magnetic fields create a sort of trap that holds the antimatter in place, preventing it from making contact with the container walls. Even with these precautions, the amount of antimatter that can be stored at any given time remains incredibly small, and the energy required to produce and store antimatter remains a significant barrier to large-scale experiments or applications. Despite these technical challenges, the pursuit of antimatter continues to be a major focus in both theoretical and experimental physics. Understanding the origins of the imbalance between matter and antimatter was one of the central goals of modern cosmology and particle physics. Scientists hope that by investigating the early conditions of the universe and studying the processes that took place during the Big Bang, they can gain deeper insights into why matter came to dominate the cosmos and why antimatter is so rare. These studies could not only shed light on the mysteries of antimatter, but could also provide critical information about the fundamental forces that govern the universe. As scientists continue to explore the origins of the universe and the fundamental properties of antimatter, another fascinating cosmic phenomenon is drawing attention: neutrino storms. These storms are characterized by intense surges of neutrinos, tiny, nearly massless particles that are extremely difficult to detect. Neutrinos are produced in vast quantities during cataclysmic events such as supernovae, the explosive deaths of massive stars. When a star reaches the end of its life, it collapses under its own gravity, creating conditions that allow for the production of enormous numbers of neutrinos. These particles are ejected from the star at astonishing speeds, often approaching the speed of light. Neutrinos interact very weakly with matter, which is why they are so difficult to detect. Unlike other particles, they can travel through entire planets without being absorbed or deflected. This allows neutrinos to provide a unique window into the inner workings of stars and other cosmic phenomena. When a supernova occurs, for example, the neutrinos produced in the explosion can reach Earth long before the light from the explosion arrives. This delay gives scientists the opportunity to observe the neutrinos and study the supernova's inner processes before the more typical electromagnetic signals reach us. Neutrino storms are an essential part of our understanding of the universe's most dramatic and violent events. They offer scientists a glimpse into the core of dying stars, providing information that cannot be obtained through traditional methods of observation. These storms could help us understand the processes that govern stellar evolution and death, and they may also provide valuable insights into the fundamental forces of nature that shape the universe. As researchers continue to refine their methods for detecting neutrinos, these enigmatic particles could reveal even more about the universe's grand narrative. In conclusion, the study of antimatter, neutrinos, and other exotic cosmic phenomena continues to push the boundaries of human knowledge. From the search for primordial antimatter to the detection of neutrino storms, scientists are uncovering new and exciting clues about the universe's origins and its most fundamental processes. Though many questions remain unanswered, each discovery brings us one step closer to understanding the intricate and mysterious workings of the cosmos. With advances in technology and deeper exploration of the universe's most enigmatic phenomena, the next great breakthroughs may be just on the horizon, waiting to reveal secrets that could transform our understanding of reality itself. In the vast and unfathomable reaches of the universe, neutrinos, the nearly undetectable particles that perpetually pass through all matter, hold a special and mysterious place. These particles, while inconspicuous and elusive, could potentially give rise to extraordinary phenomena known as neutrino storms, powerful events that might be triggered by some of the most extreme astrophysical occurrences in the cosmos. Neutrino storms can originate from a variety of such extreme events, such as gamma-ray bursts, black hole formation, or even the violent collisions of neutron stars. The study of these storms, and particularly the bursts of neutrinos associated with them, has become an increasingly crucial part of modern astrophysical research, as these particles can reveal profound insights into the processes that govern stellar evolution and the high-energy dynamics at play in the universe. Neutrinos are particles that, by nature, are incredibly difficult to detect due to their extremely low interaction with matter. Their elusive nature means that most of the time, they pass through everything, including the Earth, with little to no effect. However, when massive neutrino storms occur, such as those produced by powerful events like supernova explosions, or even the collision of two neutron stars, the consequences could be far more impactful. Imagine for a moment a storm of these infinitesimally small particles flooding through our planet, traveling through it as though the planet were nothing but an invisible barrier. While most neutrinos would pass through countless atoms without any interaction at all, a significant influx could disrupt sensitive technologies and systems here on Earth. Despite their seeming harmlessness, neutrinos carry energy, and if these particles were to converge in a dense cloud, they might increase the probability of interaction with the more delicate components of our technological infrastructure. Satellites, communication systems, and even electrical grids, all of which rely on stable electromagnetic conditions to function, could experience disruptions. The immediate manifestation of a massive neutrino storm could be seen in what is known as a radiation spike. When neutrinos bombard the Earth's surface, they could interact with atomic nuclei, producing secondary particles in the process. This chain of reactions might lead to heightened radiation levels that could be detectable by various instruments designed to monitor radiation and atmospheric conditions. The result could be significant disruptions in the technology that billions of people rely on daily, from satellite communications to electrical grids, even down to the smallest electronic devices. While the direct impact on living organisms would likely be negligible, as neutrinos, due to their weak interaction with biological tissue, would have little direct effect on human health, the ripple effects would certainly be felt. Power outages, failures in communication systems, and a breakdown in the functioning of modern technological infrastructure could cause significant disruptions to daily life, potentially on a global scale. These disruptions, though stemming from the indirect consequences of a neutrino storm, would underscore the deep reliance we have on technology that is inherently vulnerable to the powerful, invisible forces of the universe. The human-scale effects of a neutrino storm may not be immediately noticeable, as the particles themselves pass through our planet largely unnoticed. However, the broader, more indirect consequences of such storms can have profound impacts. With technology being so intricately tied to the cosmic forces that govern the universe, the delicate balance between the two may become apparent in the wake of such an event. Neutrino storms are not just fascinating in the context of their direct effects, but they also open up a window into some of the most extreme cosmic events known to science. Events such as supernova explosions or the intricate dynamics of black hole formation hold the keys to understanding how the universe works on a fundamental level. By studying neutrino storms, scientists are able to gain invaluable knowledge about the inner workings of stars, the evolution of matter, and the dynamics of high-energy astrophysical events. The study of neutrino storms is also part of an ongoing and intensive research effort aimed at improving our ability to detect these elusive particles. Since neutrinos interact so weakly with matter, detecting them is an enormous challenge. However, scientists have developed advanced neutrino detectors, which are often located in environments that shield them from other forms of radiation, such as deep underground or beneath the surface of the ocean. These detectors rely on large volumes of water or ice to capture the faint signals that occur when a neutrino interacts with a particle of matter, creating a small burst of light. The goal of these detectors is twofold: to provide early warning of impending neutrino storms and to analyze the characteristics of the particles when they do arrive. Beyond these existing detectors, ongoing research focuses on designing even more sensitive equipment that can function in extreme environments, such as deep underground or in space. These detectors aim to improve the sensitivity and accuracy of neutrino detection, allowing scientists to better understand the nature of these elusive particles. Collaborative projects spanning multiple countries and continents are underway, with the aim of combining various detection techniques to create a clearer picture of neutrino behavior. As the technology advances, scientists hope to achieve a breakthrough in neutrino detection that will enable them to unravel the mysteries of these particles in greater detail. Such breakthroughs could help us understand the processes that occur inside stars, the fundamental forces at play in the universe, and even the nature of matter itself. With every step forward, we move closer to understanding these cosmic events that seem so distant and out of reach, but which, in reality, have a direct influence on the world we live in. As we move toward a better understanding of neutrino storms, another intriguing aspect of stellar evolution comes into focus: the eventual fate of stars like our Sun. When stars exhaust their nuclear fuel, they begin a slow process of transformation. A star like the Sun will eventually expand into a red giant, shedding its outer layers and leaving behind a dense core. This core becomes a white dwarf, which over billions of years slowly cools and fades, losing its brightness as it does so. This cooling process is so gradual that it takes longer than the current age of the universe itself. As the white dwarf cools, it may eventually reach a stage known as a black dwarf, a cold, dark remnant of its former self. The concept of a black dwarf star, however, is still theoretical. No black dwarf stars currently exist because the universe is too young for them to have formed yet. This elusive final stage of a star's life highlights the incredible timescales involved in stellar evolution and presents a challenge to astronomers trying to study or detect such objects. Despite their hypothetical nature, black dwarf stars are a fascinating subject of ongoing research. Their existence represents the last stage of stellar life, a stage that has yet to be directly observed. As such, they serve as a reminder of the slow, methodical progression of stars from their birth as bright beacons of light in the cosmos to their eventual fading into near invisibility. These stars embody the dynamic, ever-changing nature of the universe, a universe that is constantly evolving and transforming. While black dwarf stars may not yet be observable, their theoretical existence provides a window into the distant future of our own sun and other stars in the universe. Even in their presumed dormant state, black dwarf stars continue to exert a gravitational influence on the surrounding space. Though these stars are no longer emitting light or heat, they still possess mass and gravitational pull, which can affect nearby star systems and planetary bodies. If a black dwarf were to pass through a star system, its gravitational forces could alter the orbits of nearby planets or other celestial bodies. These gravitational interactions could destabilize the paths of orbiting planets, potentially causing them to move closer to their host star or be sent off into the void of deep space. This disruption of orbital paths could lead to catastrophic environmental changes, such as shifts in the climate or changes in temperature, making it difficult for planets to maintain stable conditions. While the black dwarf itself may be a silent, almost invisible presence in the cosmos, its effects on surrounding systems could be dramatic and far-reaching, creating a chaotic and unpredictable environment. In this way, the study of neutrino storms and black dwarf stars illustrates just how interconnected the universe is, how vast and intricate the forces that shape it are, and how much we still have to learn about the fundamental workings of the cosmos. Whether by examining the tiny, elusive neutrinos that pass through us unseen, or by contemplating the long, drawn-out death of a star, we are constantly reminded of the complex and beautiful dance of creation and destruction that occurs on scales far beyond our comprehension. As we continue to study these phenomena, the hope is that we will gain not just knowledge of the universe, but a deeper understanding of our place within it. As the cold and distant black dwarf slowly drifts through the cosmic expanse, its presence can have profound, though subtle, effects on the surrounding space. When such a dark remnant star enters the vicinity of a binary star system, where two stars orbit a common center of mass, the gravitational pull of the black dwarf could disturb the delicate equilibrium between the two stars. The tug of gravity might draw one star closer to the other, setting off a chain of unpredictable interactions. These cosmic forces could push the stars into closer proximity, potentially leading to a dramatic and violent collision. Such an event would not only result in the destruction of the stars, but could also unleash bursts of energy and radiation, altering the very fabric of the surrounding space. The gravitational interactions don't stop at stars alone. The cosmic forces exerted by the black dwarf could also disrupt the orbits of nearby celestial bodies, planets, asteroids, and comets. The gravitational pull might be strong enough to force some of these bodies into new orbits, possibly leading them to collide with other objects in the system. The sudden influx of cosmic debris and impacts could lead to increased instability in the planetary system. Planets might lose their atmospheres, oceans might be vaporized, and entire ecosystems could be wiped out in a matter of moments. Over eons, such events would contribute to the transformation of star systems, changing their structures and even halting the formation of new planets. Even in its quiet, dormant state, the black dwarf carries an unpredictable potential for destruction, illustrating how every component in the universe, no matter how seemingly inert, plays a crucial role in the grand dance of the cosmos. Black dwarf stars themselves represent a fascinating yet somber stage in the life cycle of stellar evolution. They might not exist in the universe just yet, but current theories suggest that they are the ultimate endpoint of white dwarfs, objects that are the remains of stars like our Sun, which have exhausted their nuclear fuel. When a star like the Sun reaches the end of its life, it sheds its outer layers in a dramatic process called a planetary nebula, leaving behind a dense, hot core. This core, known as a white dwarf, begins its long, slow cooling process, a cooling that will stretch across billions of years. As the white dwarf cools, it emits progressively less light and heat, its surface temperature gradually falling lower and lower. Eventually, the temperature will drop so significantly that the star will no longer be able to radiate energy in any meaningful way. It will fall below a critical threshold, becoming a black dwarf. The transition from a white dwarf to a black dwarf is expected to take an extraordinarily long time, on the order of trillions of years, far exceeding the age of our universe. It is a process so slow that it could take longer than the current estimated lifespan of the universe itself. This transition, while technically inevitable for any white dwarf, does not involve any dramatic collapse or transformation. The forces at play, specifically electron degeneracy pressure, maintain a delicate balance, preventing the white dwarf from collapsing under its own gravity. Electron degeneracy pressure arises from the quantum mechanical properties of electrons, which prevent them from being packed too closely together. It is this force that gives a white dwarf its stability, and it will continue to operate even as the white dwarf cools and darkens, maintaining the structural integrity of the star. As the black dwarf continues its existence, it will become progressively cooler and dimmer, eventually reaching a state where it is nearly indistinguishable from the background radiation of the universe. In the far-off future, as the universe continues its expansion and cools down, the black dwarf will silently drift through space, one of the last remnants of stellar material in a darkened universe. Its existence will be almost imperceptible, a silent relic of a time when stars burned bright and galaxies teemed with dynamic activity. The black dwarf will stand as a testament to the slow, inexorable passage of time, marking the end of stellar evolution in a universe where all other active processes have long since ceased. In this distant future, the black dwarf will be a cosmic fossil, a remnant of a time when the universe was filled with energetic and tumultuous events. Yet, in the grand scheme of cosmic time, these stars will have endured, maintaining a quiet persistence as they cool and fade into nothingness. The slow fading of these stars will signal the closing chapter of a universe that was once teeming with stellar activity, but now drifts into a state of perpetual darkness and stillness. Gravitational forces, such as those exerted by the black dwarf, can have profound consequences in many other parts of the cosmos as well. Tidal forces, created by the gravitational attraction between two celestial bodies, are a significant aspect of this cosmic interplay. These forces become particularly evident when two stars, for example, orbit each other. Their mutual gravitational attraction causes them to deform each other, stretching and squeezing their shapes in response to the gravitational tug of one another. This interaction can lead to the release of tremendous amounts of energy, some of which may manifest in spectacular astronomical events. One of the most dramatic outcomes of tidal forces occurs when a star is pulled too close to an extremely dense object like a black hole. As the star approaches the black hole, the difference in gravitational force between the star's closest point and its farthest point creates a tidal gradient. This differential tug of gravity becomes so intense that it can rip the star apart in a process known as tidal disruption. The shredded remnants of the star then spiral toward the black hole, generating intense bursts of radiation and energy that can be detected by astronomers across vast distances. The energy released in such events can offer vital clues to scientists studying both the black hole and the star that has been consumed. By analyzing the bursts of radiation, astronomers can gain insights into the properties of the star, its size, composition, and structure, as well as the characteristics of the black hole itself, such as its mass and spin. These observations are invaluable, providing a rare opportunity to witness the violent interaction between a massive star and one of the most enigmatic objects in the universe. Tidal forces, therefore, play a crucial role in shaping the behavior of celestial bodies, whether they are involved in dramatic collisions or subtle deformations. Whether the force is responsible for the violent disruption of a star or the slow, quiet cooling of a black dwarf, gravitational interactions remain one of the most powerful and far-reaching forces in the universe. Even in the silence of a black dwarf's long, dark existence, the cosmic forces that govern the universe continue their relentless reshaping and transforming the very fabric of the cosmos. Every moment, whether loud and dramatic or quiet and subtle, contributes to the ever-evolving story of the universe. A story that unfolds on a scale of time and space far beyond our comprehension. Tidal interactions in the cosmos hold remarkable power, influencing the dynamics of celestial bodies in ways that extend far beyond the initial understanding of their effects. These interactions, governed by the immense gravitational forces at play, can shape the formation and evolution of stars, planets, and even entire galaxies. The profound influence of tidal forces is especially evident when one star exerts its pull on another, triggering the collapse of gas and dust clouds and thus giving birth to new stars. This process is one of the many ways in which tidal forces serve as catalysts for the creation of new cosmic entities, demonstrating their role not merely as passive influences, but as active drivers of the universe's ceaseless evolution. At the core of many of the dynamic processes in space, tidal forces are vital actors, shaping the life cycles of stars, the trajectories of celestial bodies, and the intricate interactions between them. They exert a profound influence on the orbits of planets, their moons, and other smaller objects that orbit stars. One of the most powerful forces at work within the cosmos is gravity, which extends its reach far beyond the immediate neighborhood of a star or planet. Gravity's omnipresent pull can dramatically alter the orbits of celestial bodies, especially when larger objects such as neighboring planets or stars pass within close proximity. In these encounters, a massive planet might exert such a gravitational force on a smaller satellite that it can either capture it entirely, pulling it into a dangerous orbit, or eject it into the vast, cold expanse of space. This phenomenon, while spectacular in its far-reaching consequences, is just one of the ways in which the gravitational dance of celestial bodies can shape the fate of the objects caught in their orbit. Another significant force in the shaping of planetary destinies is solar radiation. As planets and their moons move through the immense field of energy radiated by their central star, the intense beams of solar radiation can strip away the protective atmospheres of smaller bodies, leaving them vulnerable to the harsh conditions of space. This phenomenon is particularly devastating for smaller bodies with weaker gravitational fields that cannot hold onto their atmospheres, which eventually leads to the loss of water and other vital elements essential for sustaining life. In a broader sense, the interaction of solar radiation with planetary systems highlights the vulnerability of celestial bodies to the extreme conditions imposed by their stars. On a more cataclysmic scale, the threat of cosmic collisions, such as asteroid or comet impacts, looms large. Traveling at incredible speeds through the solar system, these cosmic bodies can crash into planets and their moons, causing immense damage in the process. The impact of an asteroid, for example, could create a massive crater, trigger wildfires, and even bring about dramatic shifts in climate. The extinction event that wiped out the dinosaurs on Earth serves as a prime example of how such impacts can alter the environmental conditions of a planet, forever changing the course of life and evolution. In addition to the gravitational and radiation-related forces acting on celestial bodies, tidal forces can also play a critical role in the geological stability of planets. Over the course of billions of years, the gravitational interactions between a planet and its moons can generate tidal forces that cause tectonic activities, leading to volcanic eruptions, earthquakes, and other geophysical events. These processes not only reshape the surface of the planet, but they also have profound effects on the ecosystems that might be existing on these worlds, influencing the potential for life to thrive or be extinguished altogether. Moreover, the universe is not static, and neither are the forces that govern it. Rogue celestial objects, bodies that come from outside of a planetary system, can intrude unpredictably, disturbing the delicate balance of orbits and causing unforeseen consequences. These encounters could disrupt established gravitational relationships, leading to the alteration of planetary orbits or even ejections of objects from a system entirely. Such events highlight the chaos and uncertainty that exists within the cosmos, where even the most stable systems can be upended by the unexpected passage of objects from deep space. Tidal forces, however, are not simply destructive forces. They also play a crucial role in shaping the orbits and behaviors of objects within star systems. This can be visualized through the way that the moon influences the tides on Earth. Just as the moon's gravitational pull creates tidal bulges on Earth's oceans, a star exerts a similar gravitational influence on the planets, moons, and smaller bodies that orbit it. These tidal effects can stretch and elongate the objects within the star's gravitational field, creating distortions that have lasting effects on their physical and orbital properties. The stronger gravitational pull on the side of a planet or moon that faces the star results in a stretching effect, which can lead to tidal stretching. Over time, this stretching can cause dramatic changes in the shape and behavior of these celestial bodies, leading to phenomena such as volcanic activity, the formation of rings around planets, or the evolution of moons and smaller planets. As these tidal forces continue to act over long periods of time, they can also alter the orbits of moons and other celestial objects. In certain cases, these objects may gradually spiral inward or outward as their orbits adjust to the changing gravitational influence of the star. Similarly, these forces can impact the speeds at which objects orbit, leading to synchronized orbits in which moons or smaller planets dance in close formation over time. Such complex interactions can also lead to a gradual dissipation of energy, a process that can slow down the rotation of orbiting bodies. This energy loss can eventually result in tidal locking, a phenomenon in which one side of a planet or moon perpetually faces the star, creating a permanent day on one side and a permanent night on the other. These tidal interactions, in turn, influence the potential for life on other worlds. As planets and moons become tidally locked, the extreme differences between their two sides, one bathed in constant sunlight and the other in perpetual darkness, may present unique challenges for any potential ecosystems. However, the processes initiated by tidal forces can also create habitable environments in other ways. For instance, the heat generated by tidal forces could provide an energy source for subsurface oceans, or for the formation of complex geological features that might support life. The intricate relationship between gravity, distance, and tidal interactions thus plays a crucial role in shaping not only the physical characteristics of celestial bodies, but also their potential to support life. Turning to a more speculative yet fascinating aspect of cosmic physics, we encounter the idea of axions. These hypothetical particles were proposed to resolve certain theoretical issues in particle physics, particularly those related to the strong nuclear force. Axions are imagined as extremely light, elusive particles that carry no electric charge and interact very weakly with other particles. Despite their subtlety, axions could hold the key to unlocking one of the universe's greatest mysteries, dark matter. This mysterious substance, which makes up a large part of the universe, has been detected only through its gravitational effects, as it does not emit, absorb, or reflect light, making it entirely invisible. In the search for dark matter, axions offer a potential explanation for some of the phenomena that current models struggle to account for. If axions exist, they could interact with other particles in extremely rare and difficult to detect ways. One proposed manifestation of these interactions is the concept of axion quakes. These quakes are not literal seismic events, but instead disturbances created by axion-like particles interacting with systems such as superfluid helium or other condensed matter systems. These interactions could generate disturbances that mimic the effects of seismic waves, creating measurable signals that could offer new insights into the nature of axions and dark matter. The detection of these quakes could represent a groundbreaking breakthrough in our understanding of the universe. By observing these disturbances, scientists might be able to confirm the existence of axions, providing a crucial piece of the puzzle in the search for dark matter. Furthermore, understanding how axions interact with other particles could lead to new revelations about the fundamental structure of the cosmos, offering a deeper understanding of the forces that govern everything from the smallest subatomic particles to the largest galactic formations. In the context of axion research, several approaches have been proposed to detect these elusive particles and the potential quakes they might generate. One method involves observing the behavior of light in strong magnetic fields, as axions might convert into photons under certain conditions. This conversion could reveal itself through anomalies in the way light behaves around distant galaxies or in the cosmic microwave background radiation. Another promising avenue for discovery lies in the study of neutron stars, highly magnetized celestial objects where the extreme conditions could facilitate the creation of axions. Detecting variations in the emitted radiation from these stars could provide further evidence of axion interactions. In addition to these astronomical observations, experiments on Earth aim to replicate the high-energy conditions that could produce axions. Sensitive detectors placed in isolated environments might catch rare signals indicative of axion activity. Furthermore, high-energy particle colliders, where particles are smashed together at incredible speeds, could also serve as experimental setups to search for axions, with the energy from the collisions potentially generating these elusive particles. Ultimately, the pursuit of axion research represents a multifaceted approach to one of the most enduring mysteries in science, the nature of dark matter. Through a combination of astronomical observations and particle physics experiments, scientists hope to piece together a comprehensive understanding of axions and their potential role in the structure of the universe. By confirming the existence of axions, humanity could open the door to entirely new realms of astrophysical discovery, reshaping our understanding of the cosmos and the very nature of the forces that govern it.